dust streaming outward from its central regions. This phenomenon, known as a galactic superwind, is driven by the collective energy of thousands of massive, young stars and supernovae. The superwind is composed of ionized hydrogen, oxygen, and other elements, which are ejected into the intergalactic medium at speeds exceeding 1,000 km per second. These outflows are not only visually spectacular but also play a crucial role in the evolution of the galaxy. By expelling gas and dust, the superwind limits future star formation within the system and enriches the surrounding intergalactic environment with heavy elements. The starlight forge has a highly irregular and distorted shape, making it an atypical member of the galactic family. Its elongated structure and chaotic morphology are likely the result of gravitational interactions with its neighboring galaxy, M81. The two galaxies are part of the M81 group, a small collection of galaxies bound together by gravity. Over the past few hundred million years, the gravitational forces between M82 and M81 have triggered tidal interactions that have stirred up the gas and stars within both systems. These interactions are thought to have initiated the intense starburst activity within the Torch galaxy. A distinctive feature of the smoldering spiral is its central region, where a supermassive black hole resides. This black hole, millions of times the mass of the Sun, influences the dynamics of the galaxy's core. Observations in multiple wavelengths, including X-rays, radio, and infrared, have revealed the presence of an active galactic nucleus, AGN, at the heart of the galaxy. The AGN emits high-energy radiation, which interacts with the surrounding matter and contributes to the overall energy output of the system. This interaction is another factor driving the extreme conditions within the Ember galaxy. In addition to its superwind and starburst activity, the glowing inferno is notable for its complex magnetic field. Studies using polarized radio observations have revealed large-scale magnetic structures extending outward from the galaxy's central regions. These magnetic fields are believed to play a role in shaping the galactic superwind and influencing the distribution of cosmic rays. Understanding the interplay between magnetic fields and galactic dynamics is a key area of research in modern astrophysics, and the Flame Nebula provides an excellent laboratory for studying these phenomena. The radiant rift is also a prolific source of cosmic rays and high-energy particles. Observations in gamma rays and X-rays have shown that the galaxy's core is teeming with energetic phenomena. These emissions are associated with the intense star formation and supernova activity occurring within the system. Cosmic rays generated in the galaxy's core propagate outward, interacting with the interstellar medium and contributing to the overall energy budget of the surrounding space. One of the most significant discoveries about the bright beacon came from observations in the infrared spectrum. Using advanced space-based telescopes such as the Spitzer Space Telescope and the Hubble Space Telescope, astronomers have mapped the distribution of dust and molecular gas within the galaxy. These studies have revealed a complex network of filaments and clumps, where star formation is occurring at an extraordinary rate. Infrared observations have also provided insights into the temperature, composition, and dynamics of the interstellar medium, shedding light on the processes driving the galaxy's starburst activity. The starfire expanse is not just a spectacle of astrophysical phenomena but also a key player in the cosmic ecosystem. The materials ejected in its superwind, including heavy elements like carbon, oxygen, and iron, enrich the intergalactic medium and contribute to the chemical evolution of the universe. These elements are the building blocks of planets, life, and other galaxies, making the galaxy's activity a crucial part of the cosmic cycle. In recent years, the beacon of creation has been the focus of numerous studies using advanced observatories and instruments. Telescopes like the Chandra X-ray Observatory, the Very Large Array, and the James Webb Space Telescope have provided high-resolution data across multiple wavelengths, allowing researchers to study the galaxy in unprecedented detail. These observations have not only deepened our understanding of the galaxy itself but also provided valuable insights into the broader processes of galaxy evolution, star formation, and cosmic feedback. Despite its relative proximity to Earth, the Cigar Galaxy continues to hold many mysteries. Questions remain about the exact mechanisms driving its starburst activity, the long-term effects of its interactions with M81, and the fate of its expelled gas and dust. As observational technology continues to advance, astronomers are likely to uncover even more secrets about this dynamic and enigmatic system. The Torch Nebula serves as a vivid reminder of the dynamic and interconnected nature of the universe. Its intense activity, dramatic outflows, and complex interactions with its environment exemplify the forces that shape galaxies and influence their evolution over cosmic timescales. For scientists and enthusiasts alike, the Stoga spiral remains a source of wonder and inspiration, a celestial beacon illuminating the complexities of the cosmos. The Cigar Galaxy, or Messier 82, remains a prime focus of astronomical studies not only for its unique features but also for the critical role it plays in unraveling the mysteries of galaxy evolution. This starburst system is a living laboratory, showcasing the dynamic interplay between gravity, star formation, and cosmic feedback on an extraordinary scale. One of the lesser discussed but equally fascinating aspects of the fiery veil is the role of supernovae in shaping its environment. Supernova explosions, the catastrophic deaths of massive stars, release immense amounts of energy and enrich the surrounding interstellar medium with heavy elements. These events also drive shock waves through the galaxy, compressing gas clouds and triggering further waves of star formation. In the case of M82, the supernova rate is significantly higher than that of typical galaxies, with a new supernova occurring approximately every 20 to 30 years. This elevated rate underscores the intensity of the starburst activity and its profound impact on the galaxy's overall structure and evolution. The Firebrand Nebula's proximity to its neighbor, the Grand Spiral Galaxy, M81, has also resulted in the transfer of material between the two systems. This gravitational interplay has created tidal streams of gas and stars that stretch across the intergalactic space between them. These streams, rich in hydrogen and other elements, act as cosmic highways for matter, fueling further activity within both galaxies. The interaction also serves as a natural experiment in galaxy dynamics, allowing researchers to study how gravitational forces influence galactic evolution over millions of years. Beyond the optical and infrared observations, the bright blaze has been extensively studied in radio wavelengths, revealing a wealth of information about its magnetic fields, cosmic rays, and neutral hydrogen distribution. Radio telescopes have detected large-scale outflows of neutral hydrogen gas, which are expelled from the galaxy's disk by the powerful galactic superwind. This process, known as galactic outflow, is a critical mechanism in regulating star formation. By expelling gas, the galaxy limits the amount of material available for future star formation, thereby moderating its growth and evolution. Interestingly, the flame rift has been found to host a unique population of massive molecular clouds, regions rich in molecular hydrogen and other complex molecules. These clouds, some of the largest observed in any galaxy, serve as stellar nurseries where the next generation of stars is born. The conditions within these clouds are extreme, with high temperatures, turbulent motions, and intense radiation fields. Studying these regions provides invaluable insights into the processes that govern star formation under such harsh conditions. The dusty inferno also exhibits an unusual pattern of chemical enrichment. Observations of the outflows have shown that the ejected material is not evenly mixed but rather stratified, with lighter elements being pushed out further than heavier ones. This stratification is a direct result of the physics of the galactic superwind, where lighter ions are more easily accelerated by the energy of supernovae and young stars. This phenomenon provides a unique opportunity to study the chemical evolution of galaxies and the dispersal of elements into the intergalactic medium. Another key area of study in the glimmering hearth is the interaction between its central supermassive black hole and the surrounding matter. Observations in X-rays and gamma rays have revealed evidence of high-energy phenomena occurring in the vicinity of the black hole. These include the acceleration of particles to near-light speeds and the generation of relativistic jets, which can extend thousands of light-years into space. These jets, although less prominent than those in some active galaxies, still contribute to the overall energy dynamics of the system and influence the behavior of the surrounding gas and dust. In the far-infrared spectrum, the starlight blaze reveals the presence of warm dust heated by intense radiation from young, massive stars. This warm dust emits light at wavelengths invisible to the human eye but detectable by specialized instruments. The distribution of this dust, along with its temperature and composition, provides clues about the starburst activity and the conditions within the galaxy. Infrared studies have also identified regions of intense star formation hidden behind thick clouds of dust, which would otherwise remain obscured in visible light. The halo flame, the extended halo of gas and stars surrounding M82, is another area of intense scientific interest. This halo, composed of both old stars and newly ejected material, is a direct result of the galaxy's turbulent history. The halo contains streams of stars pulled from the galaxy by tidal interactions, as well as gas and dust expelled by the galactic superwind. Studying this halo offers a glimpse into the long-term effects of the starburst activity and the galaxy's interactions with its environment. Finally, the cigar cluster, the system's broader galactic neighborhood, provides context for understanding its evolution. The M81 group, which includes M82, M81, and several smaller galaxies, is a microcosm of cosmic interactions. The gravitational interplay within this group has led to the formation of tidal bridges, gas streams, and other structures that illustrate the interconnected nature of the universe. By studying the cigar galaxy in the context of its galactic group, astronomers can better understand the processes that shape galaxies and drive their evolution over billions of years. The cigar galaxy remains a shining example of the universe's complexity and beauty. Its dynamic nature, rich structure, and profound impact on its surroundings make it a cornerstone of modern astrophysical research. As telescopes and observational techniques continue to improve, the secrets of this remarkable galaxy will undoubtedly yield even deeper insights into the fundamental workings of the cosmos. The dynamic evolution of the cigar galaxy, or Messier 82, continues to challenge and expand our understanding of galactic processes. Its uniqueness lies not only in its dramatic starburst activity but also in the interplay of forces that define its structure, behavior, and influence on the surrounding universe. Researchers have identified several emerging areas of interest that further highlight the intricacies of this galactic marvel. The superwind phenomenon in the Torch Nebula is a crucial example of feedback in galaxy evolution, a process where energy and matter expelled from the galaxy interact with its surroundings. This feedback regulates the star formation cycle by dispersing gas and dust, while also enriching the intergalactic medium. Recent observations suggest that the superwind in M82 extends far beyond the central regions, reaching distances of over 10,000 light-years. These winds are now known to influence nearby galaxies, including M81, by injecting energy and redistributing materials into their shared environment. Researchers have also discovered that these winds are not uniform. Instead, they form intricate, layered structures with varying densities, temperatures, and velocities. The interactions between different layers of the outflow generate shock waves and turbulence, which further modify the surrounding medium. By studying these outflows in detail, scientists are uncovering the complex mechanisms that govern galactic feedback and its role in shaping both individual galaxies and larger-scale cosmic structures. The ongoing starburst activity in the starlight furnace occurs under conditions far more extreme than those in typical galaxies. The central regions of the galaxy, where the most intense star formation takes place, are characterized by extraordinarily high pressures, temperatures, and radiation levels. These conditions create a unique environment for the birth of stars, leading to the formation of massive stellar clusters with populations of hot, short-lived stars. One of the most intriguing aspects of this process is the role of turbulence in compressing gas clouds to trigger star formation. The chaotic flows of gas and dust within the galaxy create regions of high density where gravitational collapse occurs. However, this turbulence also acts as a double-edged sword, dispersing some gas clouds before they can form stars. Understanding this balance between compression and dispersal is a key challenge in astrophysics, and the Ember spiral provides an ideal testbed for exploring these dynamics. Magnetic fields play an often overlooked but vital role in the evolution of galaxies, and the fiery haven is no exception. Observations using radio telescopes have revealed that M82’s magnetic fields are closely aligned with the structures of its galactic outflows. These fields act as channels, guiding the movement of charged particles and shaping the morphology of the superwind. Additionally, magnetic fields help to regulate the flow of cosmic rays, which are high-energy particles produced by supernovae and other energetic processes within the galaxy. The interplay between magnetic fields and starburst activity is an active area of research. Scientists are investigating how these fields influence the distribution of gas and dust, as well as their role in supporting or suppressing star formation. By mapping the magnetic field structures in detail, researchers hope to uncover the underlying physics that governs these interactions. The study of the Blaze Nebula has benefited immensely from advancements in multi-wavelength astronomy. Observing the galaxy across the electromagnetic spectrum, ranging from radio waves to gamma rays, has revealed a wealth of information that would be inaccessible through a single wavelength alone. For example, X-ray observations have uncovered the presence of ultraluminous X-ray sources, ULXs, within the galaxy, which are thought to be associated with black holes or neutron stars accreting matter at extraordinary rates. Infrared and submillimeter observations have provided detailed maps of the galaxy's dust content, showing how it is distributed and heated by star formation. Meanwhile, gamma-ray studies have shed light on the energetic processes occurring in the galaxy's core, including the production of high-energy particles and their interactions with the surrounding medium. This multi-wavelength approach has transformed our understanding of the galaxy, highlighting the importance of combining data from different parts of the spectrum to gain a comprehensive view of complex astrophysical systems. Beyond its immediate environment, the Starfire Rift has a far-reaching influence on the cosmic web of galaxies. The materials ejected in its superwind, particularly heavy elements such as carbon, oxygen, and iron, contribute to the chemical enrichment of the intergalactic medium. These elements are essential for the formation of planets, complex molecules, and eventually, life itself. In this way, the galaxy's activity plays a crucial role in the broader evolution of the universe, seeding the cosmos with the building blocks of matter. Moreover, the interactions between M82 and its galactic neighbors provide insights into the processes that drive galaxy clustering and group dynamics. The tidal forces exerted by M81 and other members of the M81 group have not only shaped the structure of the radiant furnace but also triggered its intense starburst activity. These interactions serve as a microcosm of the larger-scale processes that govern the formation and evolution of galaxy clusters. As technology continues to advance, the bright inferno remains a focal point for cutting-edge astronomical research. Next-generation telescopes such as the James Webb Space Telescope, JWST, and the Extremely Large Telescope, ELT, promise to deliver even more detailed observations of this enigmatic galaxy. These instruments will allow scientists to probe the smallest scales of star formation, map the distribution of elements in unprecedented detail, and explore the galaxy's interactions with its environment at higher resolutions. Additionally, the development of advanced computational models is enabling researchers to simulate the evolution of the Flame Nebula and other starburst galaxies. These simulations, informed by observational data, provide a powerful tool for testing theories of galaxy formation and evolution. By comparing the results of these models with real-world observations, scientists can refine their understanding of the physical processes at work. In many ways, the Cigar Galaxy serves as a cosmic beacon, illuminating the forces that shape galaxies and drive their evolution. Its fiery outflows, intense starburst activity, and complex interactions with its surroundings offer a vivid portrait of the dynamic universe we inhabit. As we continue to study this remarkable system, it reminds us of the intricate and interconnected nature of the cosmos, where every galaxy is both a product of its environment and a contributor to the greater cosmic tapestry. The discoveries yet to be made in the Stoga Nebula promise to deepen our appreciation of the universe's beauty and complexity, inspiring future generations of scientists and explorers to unravel its secrets. The Cigar Galaxy, with its chaotic and vibrant processes, is also a remarkable laboratory for studying how starburst activity affects the long-term evolution of a galaxy. Its rapid production of new stars comes at a cost, as the massive stellar feedback is gradually depleting the supply of gas required for future star formation. Observations indicate that much of the gas expelled in the superwind escapes the gravitational pull of the galaxy, venturing into the surrounding intergalactic medium. This process not only transforms the internal dynamics of the galaxy but also has a significant impact on its future trajectory as a star-forming system. The central regions of the galaxy, where the starburst activity is concentrated, reveal a wealth of details about the processes occurring in such environments. These regions are dominated by clusters of young, massive stars, which emit intense ultraviolet radiation and stellar winds. The radiation pressure from these stars, combined with the mechanical energy from stellar winds, creates powerful bubbles of ionized gas that expand outward, merging into the larger-scale galactic superwind. This feedback process is critical for regulating the density and temperature of the interstellar medium, influencing where and when new stars can form. One of the remarkable aspects of this galaxy is the intricate interaction between gravity, turbulence, and radiation in shaping its structure. Gravitational interactions with M81 have created tidal streams and disrupted the distribution of gas and stars, resulting in a highly irregular morphology. Meanwhile, turbulence generated by supernova explosions and stellar winds acts on smaller scales, compressing gas in some regions while dispersing it in others. These competing forces create a dynamic equilibrium that governs the overall behavior of the galaxy. The chemical enrichment observed in the expelled gas and dust provides a unique insight into the life cycle of matter in the universe. The superwind carries with it the byproducts of nuclear fusion within stars, including heavy elements such as carbon, nitrogen, and oxygen. These elements, created in the cores of stars or during supernova explosions, are essential for the formation of planets and organic molecules. By expelling these materials into the intergalactic medium, the galaxy contributes to the ongoing chemical evolution of the cosmos, ensuring that future generations of stars and planets are enriched with the building blocks necessary for complexity in life. The halo surrounding the galaxy is another fascinating feature, serving as a reservoir of both old stars and newly ejected material. This halo extends far beyond the visible disk of the galaxy, blending into the larger environment of the M81 group. Studies of this halo reveal that it contains a mix of stellar populations, including stars stripped from the galaxy by tidal interactions and those formed in situ from expelled gas. The interplay between the halo and the galaxy itself provides valuable clues about the processes that shape the outer regions of galaxies and their connections to the larger cosmic web. The role of cosmic rays in the dynamics of the galaxy is an area of active research. These high-energy particles, generated by supernova explosions and other energetic events, interact with the magnetic fields and gas in the galaxy, influencing the behavior of the superwind. Observations suggest that cosmic rays may help to accelerate the outflow of gas, providing additional energy to drive the material into intergalactic space. Understanding the contribution of cosmic rays to galactic feedback is an important step toward building a complete picture of how galaxies evolve over time. The interaction between the central supermassive black hole and its surrounding environment is another key aspect of the galaxy's dynamics. While the black hole in the Cigar Galaxy is not as active as those in some other galaxies, it still plays a significant role in shaping the core of the system. Observations in X-rays and other wavelengths indicate that the accretion of material onto the black hole produces energetic outflows and radiation, which can influence the behavior of gas and stars in the central regions. These processes are part of a complex feedback loop that regulates the growth of the black hole and the starburst activity in the galaxy. The study of this galaxy has also highlighted the importance of large-scale structures in the universe. The interactions between the Cigar Galaxy and its neighbors, particularly M81, demonstrate how galaxies within a group can influence each other over billions of years. These interactions are responsible for triggering the starburst activity in the Cigar Galaxy, as gravitational forces compress its gas and disrupt its equilibrium. By studying these processes in detail, astronomers can gain a better understanding of how galaxies evolve within the context of their larger cosmic environments. Advancements in observational technology have allowed scientists to probe the galaxy in unprecedented detail, revealing structures and processes that were previously invisible. Instruments like the Atacama Large Millimeter/Submillimeter Array, ALMA, have provided high-resolution maps of the galaxy's molecular gas, showing how it flows and accumulates in regions of intense star formation. These observations have revealed a surprising level of complexity, with gas streams, filaments, and clumps interacting in ways that challenge existing models of galaxy dynamics. The ongoing study of the Cigar Galaxy is not only revealing new insights about this specific system but also providing a deeper understanding of the fundamental processes that govern galaxies throughout the universe. By examining the intricate interplay of forces within this starburst galaxy, scientists are uncovering the mechanisms that drive star formation, regulate galactic feedback, and shape the evolution of galaxies over cosmic timescales. The discoveries made in this system are helping to build a more complete picture of the universe, one that highlights the interconnected nature of all its components. The Cigar Galaxy continues to mesmerize astronomers and enthusiasts alike, standing as a beacon of cosmic drama and complexity. Its very existence challenges preconceived notions about how galaxies evolve and thrive under the universe's most chaotic conditions. Every detail of its fiery heart and windswept edges invites a deeper exploration, pulling us into the intricate ballet of gravity, turbulence, and creation. The galaxy's starburst activity is not just an isolated marvel, it is a cosmic performance on a grand scale. Imagine billions of stars igniting in rapid succession, their collective brilliance radiating outward, flooding the surrounding space with light, heat, and energy. The sheer scale of this activity is almost incomprehensible, a relentless wave of creation and destruction unfolding across tens of thousands of light-years. This celestial furnace is not merely producing stars, it is forging the building blocks of future galaxies, solar systems, and potentially even life itself. Delving deeper into the superwind phenomenon, one can imagine the sight of colossal plumes of glowing gas and dust erupting from the galaxy's core, stretching far into the surrounding space. These outflows, driven by the energy of countless supernovae and stellar winds, are cosmic storms of unimaginable power. They carry with them not just the raw materials of stars, but also the fingerprints of the processes that created them, heavy elements forged in the hearts of dying stars, now cast out into the universe to seed new generations of celestial wonders. As we peer closer at the galaxy's central regions, a hidden world of turbulence and brilliance emerges. Clouds of gas swirl in chaotic eddies, illuminated by the intense ultraviolet radiation of young, massive stars. The interplay of light and shadow creates an ever-changing tapestry, where dense regions collapse under gravity to form new stars, only to be torn apart by the very forces they create. This cycle of creation and destruction is a testament to the dynamic nature of the cosmos, where nothing remains static, and everything is in a state of constant evolution. The galactic core itself is a cauldron of extremes, a region where the rules of physics are pushed to their limits. Here, the supermassive black hole exerts its influence, subtly shaping the behavior of gas and stars around it. While less active than the black holes in some other galaxies, this gravitational giant is a silent architect, subtly orchestrating the flow of matter in its vicinity. High-energy jets and radiation from the black hole interact with the surrounding material, adding yet another layer of complexity to this already intricate. Even beyond the visible boundaries of the influence of the Cigar Galaxy can be felt. The expelled material from its superwind does not simply vanish, it forms a vast halo of enriched gas and dust, a cosmic bridge connecting the galaxy to its neighbors and the wider universe. This halo, a faint but vital extension of the galaxy, is a reminder that no part of the cosmos exists in isolation. The materials ejected from the galaxy today may one day become the seeds of new stars and galaxies in a distant corner of the universe. The gravitational dance between the Cigar Galaxy and its neighbor, M81, adds yet another layer of fascination. Their close encounters have left visible scars, tidal streams of stars and gas that weave between the two systems, evidence of their mutual influence over millions of years. These interactions are not destructive but transformative, fueling the intense starburst activity in the Cigar Galaxy while reshaping the structure of both galaxies. It is a reminder that even in the vast emptiness of space, galaxies are connected, their fates intertwined in a grand cosmic narrative. In this ongoing story of fire and transformation, the Cigar Galaxy stands as both a mystery and a promise. It is a snapshot of the universe in flux, a place where the boundaries between chaos and order blur, revealing the raw power and beauty of cosmic creation. As we gaze at this galactic masterpiece, we are reminded of our place in the universe, not as distant observers, but as participants in a story that began billions of years ago and continues to unfold around us. Every new observation of the torch spiral uncovers more layers of its complex nature, fueling the imagination and deepening our sense of wonder. What lies hidden in its swirling clouds of gas and dust? What secrets does its superwind carry into the vastness of space? And what role does it play in the grander scheme of cosmic evolution? These questions beckon us to explore further, to push the boundaries of what we know, and to embrace the unknown. The Cigar Galaxy is not merely an object of study, it is an invitation to dream. It ignites our curiosity, reminding us that the universe is far larger, more dynamic, and more intricate than we can ever fully comprehend. Its glowing core, erupting outflows, and turbulent star nurseries call to us, urging us to look closer, think deeper, and imagine the possibilities that lie hidden among the stars. The story of this galaxy is far from over, and as we uncover more of its secrets, it continues to remind us that the universe is an endless wellspring of inspiration, waiting to be explored. The Cigar Galaxy continues to captivate with its untamed energy, pushing the limits of what we know about the universe. Its very essence is a paradox, a place of both destruction and creation, where chaos gives rise to order and stars are born in fiery cataclysms. The closer we look, the more we realize how deeply interconnected this galaxy is with its environment and how its actions ripple across cosmic distances, influencing the very fabric of the universe. Its superwind, like a galactic exhalation, is a force of staggering power. Within it, streams of ionized gas and heated dust collide and interact, creating shock fronts that glow with an eerie, ethereal light. These winds don't just carry material, they carry stories. Every particle expelled tells the tale of its origin, forged in the core of a dying star, shaped by the explosive force of a supernova, and now cast into the intergalactic medium as part of a grand cosmic recycling process. What makes the superwind even more fascinating is its dual nature. On one hand, it strips the galaxy of the very resources it needs to sustain its starburst activity. On the other, it enriches the surrounding space, sowing the seeds for new structures, new stars, and even new galaxies far beyond M82’s borders. As we venture deeper into the galaxy's core, we uncover a realm where gravity and radiation wage a constant battle. In this volatile region, massive molecular clouds twist and churn, their dense interiors acting as cradles for embryonic stars. These clouds are not passive, they are alive with activity, illuminated from within by the ultraviolet light of newly formed stars, which pierce through the surrounding dust like searchlights in a fog. The sheer density of this central region, with stars packed together thousands of times more tightly than in the Milky Way, creates a cauldron of activity that is both breathtaking and overwhelming. Amidst this intensity, we find traces of remarkable symmetry hidden within the chaos. Magnetic fields, like invisible threads, stretch across the galaxy, guiding the movement of charged particles and shaping the flow of its superwind. These magnetic fields act as architects, subtly influencing the galaxy's structure and behavior. They help channel cosmic rays, accelerate particles to near-light speeds, and regulate the distribution of gas, adding yet another layer of complexity to an already multifaceted system. Beyond the central chaos lies the extended halo, a region that, while less active, is no less intriguing. This diffuse envelope of gas, dust, and stars serves as both a record of the galaxy's history and a glimpse into its future. Within the halo are remnants of past interactions, tidal streams torn from the galaxy by gravitational encounters with M81, ancient stars scattered like breadcrumbs tracing the paths of these cosmic dances. This halo also acts as a bridge, connecting M82 to its surroundings and to the larger cosmic web of galaxies. The relationship between the Cigar Galaxy and its neighbor, M81, continues to provide new insights into the nature of galactic interactions. Their gravitational embrace is a slow, cosmic waltz, one that has unfolded over millions of years and left both galaxies forever changed. For M82, these interactions have acted as a spark, igniting its starburst activity and reshaping its structure. For M81, they have led to the formation of intricate tidal streams and filaments, adding to the tapestry of their shared environment. This interplay is not merely a local phenomenon, it mirrors the behavior of galaxies on a larger scale, offering clues about how galaxy clusters form and evolve. The cosmic rays emanating from the Cigar Galaxy add an almost otherworldly dimension to its character. These high-energy particles, born in the violent aftermath of supernova explosions, travel vast distances, carrying with them the energy of the events that created them. As they interact with the galaxy's magnetic fields and surrounding gas, they leave behind subtle signatures that tell the story of their journey. These interactions produce gamma rays and other high-energy emissions, providing astronomers with a window into processes that would otherwise remain invisible. Recent observations have also revealed unexpected phenomena in the galaxy's outskirts, where faint streams of gas and stars extend far beyond the visible boundaries. These streams, remnants of past tidal encounters, are not merely leftovers, they are active participants in the galaxy's ongoing evolution. They act as reservoirs of material that can be drawn back into the galaxy, fueling future star formation and contributing to the cycle of activity that defines M82. At the same time, these streams connect the galaxy to its environment, highlighting the interconnected nature of the universe. The Cigar Galaxy's influence extends even beyond its immediate surroundings, shaping the behavior of the intergalactic medium on a scale far larger than its physical size. The heavy elements it expels through its superwind become part of the cosmic chemical cycle, enriching the gas that permeates the space between galaxies. These elements, essential for the formation of planets and life as we know it, are carried across vast distances, ensuring that the galaxy's legacy endures long after its starburst activity fades. What truly sets the Cigar Galaxy apart is its ability to continually surprise and inspire. With every new observation, new questions arise, driving scientists to explore deeper and think more creatively about the universe and its workings. What mechanisms sustain such an intense starburst for so long? How will the galaxy evolve after its supply of gas is exhausted? And what does its story tell us about the fate of other galaxies, including our own? The answers to these questions lie in the data yet to be collected, the theories yet to be tested, and the discoveries yet to be made. As we continue to study this extraordinary galaxy, it reminds us that the universe is far from static. It is a place of constant motion, transformation, and discovery, a boundless frontier where every answer leads to new mysteries, and every observation reveals a deeper truth. The Cigar Galaxy stands as a testament to the universe's infinite complexity and beauty. It is not just an object of study, it is a cosmic symphony, a dynamic masterpiece that speaks to the interconnectedness of all things. To explore it is to embark on a journey into the heart of creation itself, a journey that promises to redefine our understanding of the cosmos and our place within it. The Cigar Galaxy, with its ceaseless dynamism, invites us to imagine the forces that have shaped it into one of the universe's most dramatic spectacles. It is a cosmic paradox, a place where the violent forces of destruction coexist with the nurturing processes of creation, where the fabric of space is constantly torn apart and rewoven by the interplay of gravity, radiation, and time. Each layer of its structure, each glowing filament of its outflows, tells a story that stretches across millions of years, a tale of transformation that continues to unfold before our eyes. The galaxy's superwind, that awe-inspiring plume of gas and dust, is more than just an energetic byproduct of its starburst core, it is a force of cosmic engineering. As this material is flung outward at extraordinary speeds, it sculpts the intergalactic environment, carving paths through the surrounding medium and creating turbulent regions where gas densities fluctuate wildly. These disruptions ripple outward like waves on a cosmic ocean, their echoes reshaping the galaxy's outskirts and even influencing the broader M81 group. The sight of this superwind, radiating in hues of red and gold as ionized gas interacts with the surrounding space, is a vivid reminder of the sheer scale and power of the processes at work. Deeper within the Cigar Galaxy lies a crucible of stellar birth unlike anything found in the Milky Way. Here, the interstellar medium is not the quiet nursery of stars but a roaring inferno of activity, where gas and dust are compressed, heated, and blasted apart in a never-ending cycle. Massive molecular clouds, the raw material for star formation, are constantly buffeted by the winds of young stars and the shockwaves of supernovae. These clouds fragment and collapse in unpredictable ways, creating clusters of stars that range from diminutive red dwarfs to gargantuan blue giants. In this chaotic environment, stars live fast and die young. The most massive among them burn through their nuclear fuel in mere millions of years before exploding as supernovae, releasing enormous amounts of energy and scattering the elements forged in their cores. These explosions, though violent, are essential to the galaxy's evolution. They seed the surrounding gas with heavy elements, providing the ingredients necessary for the formation of planets, complex molecules, and, eventually, life. At the same time, the shock waves from these supernovae compress nearby gas clouds, triggering new waves of star formation. This cycle of destruction and creation drives the galaxy's extraordinary starburst activity, sustaining it across cosmic timescales. At the heart of this chaos lies a supermassive black hole, millions of times the mass of the Sun. While not as luminous as the active galactic nuclei found in quasars, this black hole exerts a subtle but profound influence on the galaxy. Its immense gravity shapes the motion of stars and gas in the central regions, while its occasional outbursts of energy, caused by the infall of matter, create ripples that propagate outward. These ripples interact with the surrounding material, adding yet another layer of complexity to the galaxy's already turbulent dynamics. The interplay of forces within the galaxy is further complicated by the presence of large-scale magnetic fields. These fields, invisible to the human eye but detectable through their influence on charged particles, thread through the galaxy like an unseen skeleton. They guide the flow of gas and dust, influence the formation of stars, and shape the structures of the galactic superwind. Recent studies have revealed that these magnetic fields extend far beyond the visible boundaries of the galaxy, forming bridges that connect M82 to its neighbors. This discovery underscores the interconnected nature of the universe, where even the most distant objects are linked by unseen forces. Beyond the central regions, the Cigar Galaxy's halo offers a quieter but no less fascinating view of its ongoing evolution. This diffuse envelope of gas and stars is a repository of history, containing remnants of past interactions, ancient stars ejected from the galaxy's core, and streams of material torn away by gravitational encounters with M81. The halo is also a stage for the interaction between the galaxy and the intergalactic medium, where outflows of gas mix with the surrounding environment, enriching it with the elements needed to form new stars and galaxies. The relationship between M82 and M81 remains one of the most compelling aspects of the Cigar Galaxy story. These two galaxies, locked in a gravitational embrace, have influenced each other in profound ways over the course of their shared history. Their interactions have triggered tidal forces that have stretched and warped their structures, ignited bursts of star formation, and created vast streams of gas and stars that weave through the space between them. These encounters are a microcosm of the processes that shape galaxy clusters and groups, offering a window into the larger-scale dynamics of the universe. The Cigar Galaxy's influence extends far beyond its immediate surroundings. Its superwind, carrying enriched material into the intergalactic medium, contributes to the cosmic cycle of matter. The heavy elements ejected by M82, carbon, oxygen, iron, and others, become part of the universal inventory, forming the building blocks of future stars, planets, and even life. This process, known as chemical enrichment, is one of the fundamental mechanisms by which the universe evolves, transforming simple hydrogen and helium into the complex array of elements found today. Observing the Cigar Galaxy is like witnessing a cosmic symphony, with each component playing its part in a grand, ever-changing composition. From the rapid-fire birth of stars to the slow drift of tidal streams, from the searing heat of the galactic core to the cool expanses of the outer halo, every element contributes to the galaxy's story. It is a story of resilience, transformation, and interconnectedness, a reminder that even in the vastness of space, nothing exists in isolation. As telescopes grow more powerful and our understanding of the universe deepens, the mysteries of the Cigar Galaxy will continue to inspire. What secrets still lie hidden within its turbulent heart? How will its story evolve over the next billion years? And what lessons can it teach us about our own galaxy, our place in the cosmos, and the forces that have shaped the universe from its earliest days? These questions drive us to look closer, think bigger, and dream further, as we strive to uncover the truths written in the stars. The Cigar Galaxy remains a symbol of cosmic intensity, an endless source of fascination and a reminder of the boundless energy that permeates the universe. Each of its features, from its central chaos to its far-reaching halo, demands further exploration, urging us to dive deeper into its mysteries and marvel at its relentless evolution. It is as though the galaxy itself is alive, its fiery heart beating with the rhythm of creation and destruction, its outflows breathing life into the surrounding cosmos. The superwind, which continues to stretch thousands of light-years into intergalactic space, is more than just a dramatic feature, it is a force that connects the galaxy to the wider universe. Like the exhalations of a giant, the winds carry molecular gas, ionized plasma, and heavy elements into the void, where they enrich and transform the intergalactic medium. This process is not merely a local phenomenon. The materials ejected from the galaxy are part of a larger cycle that shapes the evolution of the cosmos itself. In a way, the cigar galaxy acts as a cosmic alchemist, transmuting raw hydrogen into heavier elements and then scattering these treasures into the universe, where they become the seeds of future worlds. Within the galaxy's turbulent core, star formation continues at a breathtaking pace. The molecular clouds that serve as the nurseries for these stars are immense, chaotic structures, shaped and reshaped by the energy of their surroundings. These clouds are bombarded by ultraviolet radiation, stellar winds, and the shock waves of nearby supernovae, creating a dynamic and often violent environment. Yet, despite this turbulence, these regions manage to produce stars at an extraordinary rate, a testament to the resilience of the processes that govern cosmic creation. The stars born within the cigar galaxy are not ordinary. Many of them are massive, short-lived giants, burning through their fuel in a few million years before exploding as supernovae. These explosions are not just endpoints, they are beginnings. The shock waves they create compress nearby gas clouds, triggering new waves of star formation. At the same time, the heavy elements forged in their cores are scattered into the surrounding medium, enriching it with the ingredients needed for planets, moons, and even life. The galaxy's central supermassive black hole, though less prominent than those in active galactic nuclei, plays a quiet yet profound role in this cosmic theater. Its immense gravity influences the motion of stars and gas in its vicinity, while occasional infalls of matter onto its event horizon produce bursts of energy that ripple through the surrounding space. These interactions add another layer of complexity to the galaxy's core, where gravity, radiation, and turbulence combine to create an environment unlike any other. The magnetic fields threading through the galaxy are another key player in this cosmic symphony. Invisible to the eye, these fields shape the flow of gas and dust, channeling the galaxy's energy and influencing the formation of its superwind. Recent studies have revealed that these fields extend far beyond the galaxy's visible edges, forming structures that connect M82 to its environment and beyond. These discoveries highlight the unseen forces that bind the universe together, revealing a hidden architecture that shapes the behavior of galaxies on the largest scales. The tidal interactions between the cigar galaxy and its neighbor, M81, continue to leave their mark on both systems. These encounters, which began millions of years ago, have triggered waves of star formation, created streams of gas and stars, and reshaped the structure of both galaxies. For the cigar galaxy, these interactions have been a driving force behind its starburst activity, compressing its gas and igniting the rapid formation of new stars. For M81, they have created tidal tails and bridges, visible evidence of the gravitational dance that has bound these two galaxies together. The halo surrounding the cigar galaxy is a quiet yet profound reminder of its cosmic influence. This diffuse region, extending far beyond the galaxy's disk, contains a mixture of ancient stars, expelled gas, and remnants of past interactions. It is a place where the galaxy's history is written in streams of stars and filaments of gas, each one a record of an encounter, an event, or a transformation. The halo also serves as a gateway between the galaxy and the intergalactic medium, where the materials ejected by the superwind mix with the surrounding environment, enriching it with the elements of life. Cosmic rays, high-energy particles born in the aftermath of supernova explosions, add yet another layer of intrigue to the cigar galaxy. These particles, traveling at nearly the speed of light, interact with the magnetic fields and gas in and around the galaxy, producing gamma rays and other high-energy emissions. These interactions provide astronomers with a unique window into the most energetic processes in the galaxy, revealing the hidden dynamics of its core and outflows. As we continue to observe and study the cigar galaxy, we are reminded of its role as a microcosm of the universe itself. Its starburst activity mirrors the processes that occurred in the earliest galaxies, giving us a glimpse into the conditions that prevailed in the young universe. Its interactions with M81 and the larger M81 group reflect the dynamics of galaxy clusters and the forces that shape the cosmic web. Its superwind and halo illustrate the interconnectedness of galaxies, showing how each system contributes to the larger story of the universe. The cigar galaxy is not just a distant object to be observed, it is a source of inspiration, a reminder of the power and beauty of the cosmos. It challenges us to think beyond our own world, to imagine the forces that shape galaxies and stars, and to ponder the vastness of the universe and our place within it. With every new observation, every discovery, we come closer to understanding the intricacies of this extraordinary galaxy and the countless others like it that fill the cosmos. Yet, even as we uncover its secrets, the cigar galaxy continues to surprise us, its ever-changing nature a testament to the boundless complexity of the universe. The cigar galaxy, ever enigmatic and brimming with cosmic vitality, remains a marvel that defies simplicity and rewards relentless curiosity. Every corner of its vast expanse pulses with the energy of countless interactions, stellar births and deaths, gravitational dances, and the ceaseless movement of material through space. It stands as a living testament to the raw, untamed forces that shape galaxies, forging order from chaos and scattering beauty across the universe. The galactic superwind, already an iconic feature, grows in complexity the closer it is examined. Stretching tens of thousands of light-years from the galaxy's core, this colossal outflow is more than a mechanism of expulsion, it is a dynamic engine of transformation. As the ejected gas cools and interacts with surrounding matter, it forms intricate filaments and bubbles, glowing faintly as they drift through the intergalactic medium. These structures, captured in incredible detail by advanced telescopes, seem almost alive, shifting and reshaping under the influence of turbulence, radiation, and magnetic fields. Within them, new processes begin to unfold. The cooling gas begins to condense, forming dense clumps that may one day coalesce into new stars or even seed the formation of smaller satellite galaxies. The central regions of the galaxy are a realm of extremes. Here, dense molecular clouds serve as the breeding grounds for stars, their chaotic interiors illuminated by the searing radiation of young, massive stars. These stellar nurseries are turbulent, filled with swirling gas and dust that is sculpted by the immense energy pouring out from the stars they produce. The pressure in these regions is thousands of times greater than that in typical galaxies, creating a crucible where the rules of star formation are pushed to their limits. The stars that emerge from this chaos are born into an environment that is as hostile as it is fertile, where their lives are measured in millions of years, mere moments on cosmic timescales. The most massive stars, those destined to end their lives as supernovae, play a pivotal role in the galaxy's evolution. Their explosive deaths not only release tremendous amounts of energy but also send shockwaves rippling through the surrounding medium. These shockwaves compress nearby gas clouds, triggering yet another wave of star formation. This feedback loop, where destruction leads to creation, is one of the defining characteristics of the Cigar Galaxy. It ensures that the galaxy's starburst activity continues, even as it depletes the very material that sustains it. Amidst this frenzy of activity, the supermassive black hole at the galaxy's center sits as a quiet yet powerful force. Its gravitational pull shapes the orbits of stars and gas in the central regions, creating a dense, rotating disk that feeds material toward the black hole. Occasionally, as gas and dust spiral inward, they are heated to millions of degrees, emitting bursts of energy that light up the galaxy's core. These emissions, though brief, ripple outward, influencing the behavior of the surrounding gas and adding yet another layer of complexity to the galaxy's inner dynamics. The magnetic fields threading through the galaxy act as invisible architects, shaping the flow of matter and energy. Recent studies have shown that these fields are not uniform but instead form complex, layered structures that extend far beyond the galaxy's visible disk. These magnetic fields interact with the charged particles in the galaxy's superwind, creating patterns of motion that are both chaotic and ordered. They also play a role in the acceleration of cosmic rays, guiding these high-energy particles as they travel through the galaxy and beyond. The halo of the galaxy, often overlooked in favor of its more dramatic features, is a region of quiet significance. This diffuse envelope of gas and stars tells the story of the galaxy's past interactions, its material shaped and reshaped by the gravitational pull of neighboring galaxies. Streams of stars and gas, remnants of tidal encounters with M81, crisscross the halo, forming faint structures that stretch far into space. These streams are not static, they move and evolve, gradually blending into the intergalactic medium. The halo is also enriched by the material expelled in the superwind, which mixes with the older stars and gas to create a region of stunning complexity. The tidal interactions between the Cigar Galaxy and M81 continue to captivate astronomers. These encounters, which have occurred over millions of years, have left indelible marks on both galaxies. For M82, the gravitational forces exerted by its larger neighbor have stirred up its gas and dust, triggering waves of star formation and reshaping its structure. For M81, the encounters have created long tidal tails and bridges, forming intricate patterns that connect the two galaxies. These interactions are not merely a local phenomenon, they are a microcosm of the processes that shape galaxy clusters and the cosmic web. The influence of the Cigar Galaxy extends far beyond its immediate surroundings. Its superwind, carrying enriched material into the intergalactic medium, contributes to the broader process of cosmic evolution. The heavy elements it expels, carbon, oxygen, iron, and others, become part of the universal inventory, the building blocks of future stars, planets, and even life itself. This cycle of enrichment, where galaxies like M82 seed the universe with the elements of complexity, is one of the most profound processes in the cosmos. Every new observation of the Cigar Galaxy reveals additional layers of complexity, challenging our understanding of how galaxies form, evolve, and interact. From its fiery core to its wind-swept halo, from its dense star-forming regions to its quiet tidal streams, every aspect of this galaxy speaks to the interconnected nature of the universe. It reminds us that even the most distant galaxies are part of a larger whole, their actions shaping the cosmos in ways we are only beginning to understand. As we continue to study this remarkable system, the Cigar Galaxy becomes not just an object of scientific inquiry but also a source of inspiration. Its relentless energy, its capacity for renewal, and its role in the grander cosmic narrative remind us of the boundless possibilities that the universe holds. It is a beacon of discovery, a reminder that even amidst the chaos of creation, there is beauty, purpose, and an unending story waiting to be told. The Cigar Galaxy, like an eternal flame burning in the darkness of space, refuses to be silent or still. Its very existence is a declaration of the universe's creative and destructive powers, a place where matter collides, transforms, and reshapes itself on scales that defy human comprehension. It is a galaxy alive with activity, a cosmic forge where stars, elements, and entire structures are born and reformed in a never-ending cycle of cosmic alchemy. The galaxy's superwind continues to astonish astronomers with its complexity and sheer power. It is not a uniform stream of expelled matter, but a dynamic, ever-changing phenomenon filled with turbulence and structure. Within this superwind, vast streams of ionized gas swirl like ribbons of fire, glowing in vivid red and orange hues as hydrogen atoms are excited by intense radiation. Embedded within these flows are dense knots of material, regions where gas is cooling and condensing, potentially setting the stage for the formation of small satellite systems or isolated stars far from the galaxy's core. These pockets of future potential carry the essence of M82’s legacy, seeding the vast intergalactic medium with the tools for creation long after the galaxy itself has quieted. At the heart of this superwind lies the galaxy's starburst core, a region of unrivaled energy in chaos. Packed within a relatively small area, countless massive stars live out their short but brilliant lives, their combined light illuminating the entire galaxy. The gravitational interplay within this core is extraordinary, as massive molecular clouds collapse under their own weight while being simultaneously ripped apart by the immense forces around them. Here, in this maelstrom of gravity, radiation, and turbulence, stars are forged at a rate that dwarfs the star formation activity of calmer galaxies like the Milky Way. Supernovae occur frequently in this region, their explosive power reshaping the interstellar medium with each burst. These titanic explosions release energy equivalent to the total output of the Sun over billions of years, creating shockwaves that ripple through the dense gas clouds. The shockwaves compress the gas, triggering further star formation, even as they disperse and enrich the surrounding medium with elements forged in the dying star's cores. This relentless feedback cycle ensures that the starburst activity remains sustained, making the Cigar Galaxy one of the most prolific star factories in the universe. Galaxies are the grand architectural masterpieces of the universe, vast cosmic cities comprising billions or even trillions of stars, planets, nebulae, dark matter, and supermassive black holes. These celestial structures, ranging in shape from majestic spirals to enigmatic ellipticals and irregular clusters, have captivated humanity for centuries, igniting an insatiable curiosity about their origin, evolution, and destiny. Among them, the Sombrero Galaxy, or Messier 104, stands as one of the most striking and mysterious examples, a galactic enigma revealing the universe's complexity and grandeur. The Sombrero Galaxy, located approximately 31 million light-years from Earth in the Virgo constellation, earned its name due to its distinctive appearance. When viewed through telescopes, it resembles a wide-brimmed sombrero hat, thanks to its bright central bulge surrounded by a dark, sharply defined dust lane. This iconic structure represents a hybrid of galactic types, combining features of spiral and elliptical galaxies. The luminous core and large halo of globular clusters suggest an elliptical nature, while the prominent disk and dust lane highlight its spiral characteristics. This duality challenges traditional classification systems and invites deeper investigation into the processes that shape galaxies. Astronomical studies suggest that the Sombrero Galaxy is a massive object, containing roughly 800 billion solar masses. Its halo is populated by an exceptional number of globular clusters, up to 2,000, far surpassing the few hundred typically found in a galaxy like the Milky Way. This abundance raises questions about the galaxy's history and whether it formed through a series of mergers or evolved in isolation. Additionally, the Sombrero Galaxy's core harbors a supermassive black hole with a mass of about 1 billion times that of our Sun, further accentuating its role as a cosmic powerhouse. Modern astronomy relies on a combination of observational techniques and theoretical modeling to study galaxies like M104. Optical telescopes, such as the Hubble Space Telescope, provide high-resolution images, capturing the intricate details of the galaxy's structure. Meanwhile, radio telescopes delve into the cold, diffuse gas that fuels star formation, and X-ray observatories detect emissions from the hot gas swirling around its central black hole. Spectroscopy, a technique that analyzes the light spectrum emitted or absorbed by a galaxy, reveals crucial information about its chemical composition, motion, and distance. One of the most intriguing aspects of galactic research involves uncovering the role of dark matter. Observations of galaxies, including the Sombrero Galaxy, suggest that their visible mass, stars, gas, and dust, is insufficient to account for the gravitational forces required to maintain their structure. Instead, an invisible, enigmatic substance known as dark matter provides the necessary mass to hold these cosmic entities together. Studies indicate that up to 90% of a galaxy's total mass may be dark matter, yet its nature remains one of the greatest mysteries in astrophysics. The study of galaxies is not merely a pursuit of academic curiosity. It holds profound implications for understanding the universe's past and future. Galaxies are the fundamental building blocks of the cosmos, and their evolution is intricately linked to the history of the universe itself. The light we see from distant galaxies travels vast distances, allowing astronomers to peer billions of years into the past. By studying these ancient light sources, we reconstruct the timeline of the universe, from the Big Bang to the present day. The Sombrero Galaxy, with its unusual characteristics, provides a unique laboratory for exploring these cosmic questions. Its bright core offers a window into the behavior of supermassive black holes and their influence on surrounding stars and gas. The dust lane, meanwhile, serves as a site of active star formation, illustrating the cyclical nature of galactic evolution. Moreover, the halo's globular clusters may contain some of the oldest stars in the universe, offering insights into the early stages of galaxy formation. In recent years, advancements in technology have revolutionized our ability to study galaxies. Ground-based observatories equipped with adaptive optics can correct for the blurring effects of Earth's atmosphere, achieving near-space-level clarity. Space-based instruments, such as the James Webb Space Telescope, extend our reach into infrared wavelengths, penetrating the dust and gas that obscure visible light. These tools enable astronomers to study galaxies across the electromagnetic spectrum, uncovering hidden structures and processes. The exploration of galaxies also intersects with other scientific disciplines, such as cosmology and particle physics. The distribution and behavior of galaxies provide critical evidence for understanding dark energy, the mysterious force driving the universe's accelerated expansion. Observations of galactic clusters, the largest gravitationally bound structures, test theories about the nature of gravity and the large-scale structure of the cosmos. Despite these advancements, many questions remain unanswered. How do galaxies form and evolve over billions of years? What triggers the transition from active star formation to quiescence? How do interactions and mergers shape their structure? The Sombrero Galaxy exemplifies these mysteries, as its hybrid nature hints at a complex and perhaps turbulent past. Furthermore, the study of galaxies holds profound philosophical and existential implications. By examining these distant worlds, we confront our place in the universe. Galaxies are not static monuments but dynamic ecosystems, constantly evolving and interacting. They remind us that the universe is a vast, interconnected web of matter and energy, governed by the same physical laws that shape our own existence. In the coming decades, the quest to unravel the mysteries of galaxies will continue to drive innovation and discovery. Next-generation telescopes, such as the Extremely Large Telescope (ELT) and the Square Kilometre Array (SKA), promise to expand our understanding of the cosmos. These instruments will provide unprecedented resolution and sensitivity, enabling detailed studies of galaxies across cosmic time. As we gaze at the Sombrero Galaxy and its brethren, we are not merely observing distant objects. We are engaging in a profound dialogue with the universe, seeking to understand the forces that shape it and our place within it. The study of galaxies is a testament to human curiosity and ingenuity, a pursuit that transcends borders and generations, uniting us in a shared quest for knowledge and wonder. This extensive and enriched narrative captures the essence of galactic science and highlights the Sombrero Galaxy's allure and significance. Let me know if you'd like further elaboration or a specific focus on any aspect. The Sombrero Galaxy, often regarded as one of the most beautiful galaxies in the universe, is not merely an object of aesthetic fascination. It holds within it profound scientific puzzles that challenge our understanding of cosmic evolution. Imagine standing on the edge of its luminous disk, where the gravitational pull of billions of stars dances with the unseen forces of dark matter, shaping the intricate ballet of its structure. Every pinpoint of light in this galaxy represents a solar system, a potential cradle of life, and a glimpse into the vast possibilities of existence. What makes M104 particularly intriguing is the stark contrast between its bright, tightly packed central bulge and the thin, flat disk encircling it. This juxtaposition raises questions about its formation. Did it evolve in isolation, quietly accumulating mass over billions of years? Or did it endure violent encounters with other galaxies, merging and absorbing them into its structure? Theories abound, but definitive answers remain elusive, veiled behind the enigmatic glow of its stars and the cold embrace of interstellar dust. The supermassive black hole at the heart of the Sombrero Galaxy is another captivating feature. Black holes are the ultimate cosmic enigmas, regions where gravity is so intense that not even light can escape. In the case of M104, this black hole is estimated to be over 1 billion times the mass of our Sun, exerting a profound influence on its surroundings. The swirling disk of gas and dust feeding this gravitational monster emits high-energy X-rays, providing a rare glimpse into the violent processes occurring at galactic cores. These observations allow scientists to probe the relationship between black holes and the galaxies that host them, a relationship that remains one of the most profound mysteries in astrophysics. Zooming out, the halo of the Sombrero Galaxy reveals another layer of its story. This diffuse, spherical region is home to thousands of globular clusters, dense collections of ancient stars bound tightly by gravity. Each of these clusters is like a relic from the early universe, a fossilized record of the conditions that existed shortly after the Big Bang. Studying these clusters offers clues about the galaxy's formation history and the broader processes that shaped the cosmos in its infancy. Perhaps one of the most mind-bending aspects of studying galaxies like the Sombrero is the realization that we are looking into the past. The light from M104 takes 31 million years to reach us, meaning we see it not as it is today, but as it was when dinosaurs roamed the Earth. This concept, known as look-back time, transforms galaxies into time machines, allowing us to observe the universe's history unfolding before our eyes. Galaxies are not isolated islands floating in space. They are interconnected through vast cosmic structures, forming clusters, superclusters, and filaments that span millions of light-years. The Sombrero Galaxy resides near the Virgo cluster, one of the most massive galaxy clusters in the local universe. This cluster's gravitational influence, along with the mysterious push of dark energy, subtly shapes M104's trajectory. The interplay of these forces is a microcosm of the larger cosmic drama, where gravity and dark energy compete to define the universe's fate. Dark energy itself is a tantalizing concept, one that emerged from the study of galaxies. In the 1990s, astronomers discovered that the universe is not just expanding, it is accelerating. This revelation, awarded the Nobel Prize in Physics in 2011, suggests the presence of a mysterious force permeating space. Galaxies, as the visible markers of the universe's expansion, are key to unraveling this mystery. Observing how galaxies like the Sombrero move and evolve provides critical data for understanding the nature of dark energy and its implications for the ultimate destiny of the cosmos. But even as we look outward, the study of galaxies reflects back on us, forcing us to confront profound questions about our own existence. What role does Earth play in this vast cosmic tapestry? Are we an anomaly, a unique phenomenon in a universe dominated by lifeless gas and dust? Or are galaxies teeming with planets like ours, harboring lifeforms gazing back at the cosmos, wondering about their place just as we do? The Sombrero Galaxy, with its serene beauty and hidden complexities, invites us to ponder these questions. It beckons us to explore not just its physical structure, but the deeper truths it holds about the universe and ourselves. Every photon of light from its stars carries a story, a tale of creation, transformation, and endless possibility. And as our telescopes grow more powerful, as our understanding deepens, we edge closer to deciphering these tales, one galaxy at a time. The journey to uncover the secrets of galaxies like M104 is far from over. The universe is a living, breathing entity, constantly evolving and reshaping itself. The Sombrero Galaxy, though seemingly static in the cold depths of space, is part of this grand cosmic symphony, a symphony we are only beginning to understand. The more we learn, the more we realize how much remains unknown, how much wonder lies ahead. And so, we continue to look up, to question, to dream, knowing that each discovery is not an endpoint, but a new beginning. As we dive deeper into the mysteries of the Sombrero Galaxy and its kind, the questions only become more compelling. Why does this galaxy, with its serene, symmetrical structure, hold such an unusually large supermassive black hole? Could this central colossus be the key to understanding the galaxy's past? Black holes are often associated with chaos and destruction, yet in the case of the Sombrero Galaxy, it appears to contribute to a striking balance, a paradox that defies our expectations. The supermassive black hole at the core of M104 is not just a gravitational anomaly but a cosmic engine. Its immense mass allows it to control the surrounding gas, dust, and even entire stars. This process creates an accretion disk, an extraordinarily hot and bright structure formed as matter spirals into the black hole. The energy radiated by this disk is so intense that it can outshine the combined light of millions of stars. What's fascinating is how this energy can also regulate star formation, either by compressing gas clouds to trigger new stars or by blasting the surrounding area with radiation, suppressing stellar birth entirely. Understanding this delicate balance is essential for piecing together how galaxies evolve over time. The Sombrero Galaxy also serves as a cosmic time capsule. It's filled with globular clusters, holds the secrets of the early universe. These clusters are some of the oldest known structures in the cosmos, containing stars that formed when the universe was still young and dominated by primordial elements like hydrogen and helium. By analyzing the light from these ancient stars, astronomers can decode the chemical fingerprints left behind, revealing when and where they were formed. This helps scientists reconstruct not only the history of M104 but also the broader story of galaxy formation. However, the Sombrero Galaxy is not just a relic of the past, it is an active participant in the present-day cosmic web. Galaxies are not solitary wanderers, they are part of vast, interconnected structures that stretch across the universe. The Virgo supercluster, where M104 resides, is a massive node in this web, connecting filaments of dark matter, gas, and galaxies. Dark matter, although invisible, plays a crucial role in this network. It provides the gravitational scaffolding that holds galaxies together and binds them into clusters. Without dark matter, the Sombrero Galaxy, along with every other galaxy, would simply fly apart. The quest to understand led to some of the most ambitious experiments in physics. From underground detectors buried deep within mountains to particle accelerators like the Large Hadron Collider, scientists are hunting for elusive particles that could explain this unseen force. The Sombrero Galaxy's rotation curve, how its stars move at different distances from the center, offers compelling evidence for dark matter's presence. Unlike what Newtonian physics predicts, the outer stars in M104 rotate at speeds that suggest the galaxy is surrounded by a massive, invisible halo of dark matter. The Sombrero Galaxy also offers a lens into the future of our own Milky Way. In billions of years, the Milky Way and the Andromeda Galaxy are expected to collide, forming a new galactic entity. While such mergers may seem chaotic, they are part of the natural life cycle of galaxies. The Sombrero's peculiar structure, its bright core and extended halo, may be the result of a similar ancient merger, preserved in its serene appearance. By studying galaxies like M104, astronomers can predict the potential outcomes of such cosmic collisions, providing a glimpse into the distant future. Another captivating aspect of M104 is its star-forming regions, hidden within its dusty disk. Despite its old, massive halo, the Sombrero Galaxy continues to produce new stars, a testament to the dynamic processes within its structure. Star formation is not a uniform process, it requires the right conditions, a delicate interplay of gravity, temperature, and gas density. The dark dust lanes of M104, sharply etched against its luminous core, are the nurseries where these stars are born. Observing these regions in detail using infrared telescopes allows scientists to study how stars form under varying conditions, deepening our understanding of this universal phenomenon. And yet, for all its beauty and secrets, the Sombrero Galaxy reminds us of the vastness of the unknown. Its sheer scale, spanning 50,000 light-years, challenges our ability to comprehend the immensity of the universe. Within this single galaxy lie billions of stars, each potentially surrounded by planets, some of which may harbor the conditions for life. The search for extraterrestrial life is one of humanity's most profound endeavors, and galaxies like M104 provide countless opportunities for discovery. If intelligent civilizations exist elsewhere, they may also gaze upon their version of the Sombrero Galaxy, pondering their place in the cosmos as we do. The study of galaxies, including M104, is a multidisciplinary effort. Astronomers, physicists, chemists, and even biologists collaborate to unravel the complex tapestry of the universe. Instruments like the James Webb Space Telescope, JWST, have revolutionized our ability to study galaxies in unprecedented detail. With its infrared capabilities, the JWST can peer through the dust and reveal the hidden layers of the Sombrero Galaxy, uncovering new insights into its star-forming regions and central black hole. What's perhaps most thrilling is that every new discovery about galaxies like M104 opens the door to even deeper mysteries. Why do some galaxies stop forming stars while others remain active? What role do magnetic fields play in shaping their structure? And how does the interplay between dark matter and baryonic matter influence their evolution? The Sombrero Galaxy, with its iconic beauty and scientific complexity, is more than just a distant object in the night sky, it is a testament to the universe's creativity and the unyielding curiosity of humankind. It is a reminder that even as we uncover the secrets of the cosmos, the universe always keeps something more to reveal, an endless source of wonder and inspiration. And so, we look up, not just to observe, but to dream, to question, and to discover our place in this vast and astonishing cosmos. The Sombrero Galaxy is not merely a dazzling object suspended in the vast darkness of space, it is a cosmic laboratory where the laws of physics, chemistry, and cosmology converge, challenging the boundaries of human understanding. Its unique features provide an opportunity to explore some of the universe's most profound mysteries, from the nature of dark matter to the origins of supermassive black holes and even the potential for life in distant worlds. One of the most perplexing questions about galaxies like the Sombrero is the role of dark matter, the unseen mass that outweighs visible matter by a factor of about 5 to 1. Without dark matter, the rapid rotation speeds of stars in M104's outer regions would cause them to be flung into intergalactic space. Yet, they remain bound to the galaxy, circling the core as though held by an invisible hand. This phenomenon, first observed in the 20th century, was one of the key pieces of evidence for the existence of dark matter. But what is it? Is it made of exotic particles yet to be discovered? Or could it represent a flaw in our understanding of gravity itself? To explore these questions, scientists use powerful simulations. Supercomputers recreate the Sombrero Galaxy, incorporating the known laws of physics and different hypotheses about dark matter. These simulations are not mere theoretical exercises, they are predictive tools. By comparing simulated galaxies to the real M104, astronomers can refine their models, narrowing down the possible explanations for dark matter. Some theories propose particles such as WIMPs, weakly interacting massive particles, while others suggest entirely new frameworks for physics, such as modified Newtonian dynamics, MOND, or higher-dimensional effects. Beyond its dark matter halo, the Sombrero Galaxy's luminous central bulge offers a glimpse into the mysterious relationship between galaxies and their supermassive black holes. Unlike the Milky Way's black hole, which has a mass of around 4 million suns, M104's black hole tips the scales at a staggering billion solar masses. This vast difference raises critical questions. How do these behemoths grow so massive? Are they seeded by smaller black holes formed in the early universe, or do they grow primarily by consuming gas, stars, and even other black holes during galactic mergers? The black hole in M104 is remarkably quiet compared to the so-called quasars found in distant galaxies, where supermassive black holes voraciously consume matter, emitting blinding light across the universe. The Sombrero's subdued activity suggests it is in a dormant phase, but its past may have been far more dramatic. The surrounding globular clusters, relics from an earlier cosmic epoch, may hold the answers. These clusters could contain stars that bear the chemical fingerprints of intense energy outputs, such as those associated with an active black hole. Studying these clues could rewrite our understanding of galactic life cycles. The galaxy's dust lane, the dark band encircling its luminous core, is another area of intense scientific focus. These dense clouds of interstellar dust and gas are more than just visual features, they are the raw material for star formation. When gas clouds within these regions collapse under gravity, they ignite nuclear fusion, giving birth to new stars. Yet the process is far from straightforward. Magnetic fields, turbulence, and radiation pressure all compete to determine whether a star will form or the cloud will remain stable. Astronomers use advanced telescopes, such as the Atacama Large Millimeter/Submillimeter Array, ALMA, to probe these regions in exquisite detail. By observing the faint emissions from cold molecules, they can map the distribution and motion of gas in the dust lane. These observations reveal regions where new stars are likely to emerge and help answer broader questions about how galaxies like M104 sustain star formation over billions of years. But the Sombrero Galaxy does not exist in isolation. Like all galaxies, it is influenced by its environment. The interplay between galaxies and their surroundings, known as galactic ecology, is a burgeoning field of study. In the dense environment of the Virgo supercluster, gravitational interactions between galaxies can strip away gas, disrupt star formation, or trigger bursts of new activity. While the Sombrero appears relatively undisturbed, faint streams of stars or gas, known as tidal tails, could betray past encounters with smaller galaxies. These interactions are cosmic fingerprints, evidence of the dynamic forces shaping the universe on the largest scales. The Sombrero Galaxy also inspires speculation about the potential for extraterrestrial life. Within its disk, where stars are concentrated, there may be countless planets orbiting sun-like stars. Recent discoveries of exoplanets have shown that planets are more common than once believed, with many residing in the so-called habitable zone, the region around a star where conditions could support liquid water. Could some of these planets harbor life, perhaps even intelligent civilizations? If so, how would they perceive their place in the universe? And might they, like us, gaze at neighboring galaxies in awe, wondering if they are alone? The search for life extends beyond direct observation. Scientists study the chemical evolution of galaxies to understand the distribution of elements necessary for life. The Sombrero's globular clusters, for instance, contain ancient stars that formed when the universe was dominated by hydrogen and helium. Over time, nuclear fusion within stars has produced heavier elements, carbon, oxygen, nitrogen, the building blocks of life. By examining the Sombrero's chemical composition, astronomers can trace the processes that enriched its stars and planets with these life-sustaining elements. The future of galactic research promises even more profound discoveries. The next generation of telescopes, such as the Extremely Large Telescope (ELT) and the Square Kilometre Array (SKA), will provide unprecedented sensitivity and resolution. These instruments will allow scientists to study galaxies not just as they are today but as they were billions of years ago, when the first structures in the universe were forming. By observing galaxies like M104 in greater detail, we can piece together the history of the cosmos itself. The Sombrero Galaxy, with its serene beauty and hidden complexities, is a microcosm of the universe. It is a place where the forces of nature, gravity, radiation, magnetism, interact on scales both vast and minute. It is a testament to the ingenuity of humanity that we can observe and study such distant objects, deciphering their secrets from the faint light that reaches us across millions of years. And yet, for all that we have learned, the Sombrero Galaxy remains a mystery, a beacon of the unknown, urging us to continue exploring, questioning, and dreaming. The universe, it seems, always has more to reveal. The Sombrero Galaxy, despite its iconic appearance and relative proximity in cosmic terms, is a gateway to understanding phenomena that stretch the limits of human comprehension. Its features, ranging from its enigmatic supermassive black hole to its delicate dust lanes and ancient halo, are not isolated wonders but interconnected pieces of a grander cosmic puzzle. Each revelation about M104 serves as a stepping stone toward answering some of the universe's most fundamental questions, while simultaneously opening new doors of inquiry. Supermassive black holes, like the one at the center of the Sombrero Galaxy, remain one of the most perplexing and captivating phenomena in astrophysics. While these gravitational giants were once thought to be mere byproducts of galactic formation, recent studies suggest they may play a central role in shaping their host galaxies. Observations of M104 reveal a paradox: its central black hole is quiescent, yet the galaxy around it shows no signs of the violent upheaval often associated with such massive objects. Could this black hole have been more active in the past, shaping the Sombrero's structure through energetic jets and winds? Or is it lying dormant, awaiting a fresh influx of matter? Simulations of galaxy evolution have demonstrated that feedback from supermassive black holes, where high-energy radiation and winds push out surrounding gas, can regulate star formation. This process, known as AGN, active galactic nucleus, feedback, prevents galaxies from growing uncontrollably large. The Sombrero Galaxy's bright, tightly packed core suggests a history of intense activity, even if that activity has now subsided. By studying the chemical signatures in its central region, astronomers can reconstruct its history, searching for evidence of ancient outbursts that may have shaped its luminous bulge and serene outer disk. One of the most fascinating aspects of studying galaxies like the Sombrero is the field of galactic archaeology, the attempt to unravel a galaxy's history by studying its oldest components. The Sombrero's globular clusters, densely packed groups of ancient stars, are particularly valuable in this effort. These clusters are time capsules, preserving the conditions of the early universe when they first formed. By analyzing their metallicity, the abundance of elements heavier than hydrogen and helium, scientists can infer how and when the Sombrero galaxy enriched itself with heavier elements. Interestingly, the Sombrero galaxy's globular clusters show a bimodal distribution. Some are rich in heavy elements, while others are metal poor. This suggests that the galaxy may have grown through both internal star formation and external mergers with smaller galaxies. Each merger would have introduced new stars, gas, and dark matter, contributing to the galaxy's current structure. This duality makes M104 a prime example of how galaxies evolve through a combination of peaceful accretion and violent interactions. The Sombrero's prominent dust lane is not just a visual feature, it is a critical clue to its inner workings. This lane, composed of cold gas and dust, is where star formation occurs. However, unlike the well-defined spiral arms of galaxies like the Milky Way, the Sombrero's disk appears smooth and featureless. This raises intriguing questions. Is the dust lane a relic of a more active past, or is it the result of a unique process that inhibits the formation of distinct spiral patterns? Infrared observations have revealed that the dust lane contains a surprising amount of cold gas, the raw material for star formation. Yet, star formation in the Sombrero galaxy is relatively subdued compared to more active galaxies. This suggests that something is suppressing the process, possibly the influence of its central black hole or the galaxy's unique gravitational dynamics. Understanding why star formation varies so widely between galaxies, and even within different regions of the same galaxy, is a key challenge in astrophysics. Zooming out, the Sombrero galaxy is not an isolated entity but a part of the cosmic web, a vast network of galaxies, dark matter, and intergalactic gas that defines the large-scale structure of the universe. The Virgo supercluster, where M104 resides, is a bustling hub of activity, with galaxies interacting through gravitational forces. While the Sombrero appears relatively undisturbed, its history may include past interactions with nearby galaxies or even entire galaxy groups. These interactions can leave subtle imprints, such as streams of stars or gas extending from the galaxy's disk. These tidal features, though faint, are invaluable for reconstructing a galaxy's past. Observations of the Sombrero at extremely low surface brightness levels could reveal such features, offering new insights into its history of mergers and interactions. The Sombrero galaxy, like all galaxies, holds the story of the universe within its stars and structures. Its oldest stars, formed less than 1 billion years after the Big Bang, contain the chemical fingerprints of the first supernovae, which forged the heavy elements essential for life. By studying the light from these ancient stars, astronomers can trace the chemical evolution of the cosmos, linking the formation of galaxies to the broader history of the universe. Furthermore, the Sombrero's striking resemblance to a hybrid of elliptical and spiral galaxies challenges traditional classification schemes. This hybrid nature may be the result of unique conditions during its formation, providing clues about the diversity of galactic evolution. Could the Sombrero represent a transitional stage between different galactic types? Or is it an entirely unique entity, shaped by forces we have yet to understand? The Sombrero galaxy's mysteries are not merely academic, they drive technological innovation and international collaboration. Upcoming missions, such as the Nancy Grace Roman Space Telescope, aim to map the universe's structure with unprecedented detail, shedding light on dark matter and the role of galaxies like M104 in the cosmic web. Ground-based telescopes like the Extremely Large Telescope, ELT, will peer deeper into the sombrero's core, revealing the dynamics of its black hole and surrounding stars. Meanwhile, instruments like the Square Kilometre Array, SKA, will revolutionize our understanding of the intergalactic medium, the diffuse gas that connects galaxies. By studying how this gas interacts with galaxies like the sombrero, scientists hope to uncover the processes that fuel star formation and regulate galaxy growth. As we gaze at the sombrero galaxy, we are reminded of the boundless potential of the cosmos. Each discovery about M104 is not just a step forward in science, it is a testament to humanity's ability to question, to explore, and to dream. The sombrero is more than a galaxy, it is a symbol of the universe's endless capacity for wonder, complexity, and beauty. And as our tools grow more powerful and our theories more refined, the mysteries of M104 will continue to inspire the next generation of explorers, thinkers, and dreamers. The universe, vast and unfathomable, continuously reveals glimpses of its complexity, and among its celestial wonders, the Sombrero Galaxy stands out as a masterpiece of natural architecture. It beckons us not just with its beauty but with the secrets it holds, secrets that push the limits of our understanding and ignite our deepest curiosities. From the silent movements of its stars to the hidden forces shaping its evolution, the Sombrero Galaxy is a story waiting to be unraveled, a puzzle woven with threads of time, gravity, and light. Imagine standing at the edge of its luminous disk, surrounded by billions of stars, each one potentially hosting planets. The thought alone is staggering. What would those worlds look like? Could there be a planet with intelligent beings gazing back at their version of the cosmos, wondering if they too are part of something greater? The search for extraterrestrial life isn't just about finding biological traces, it's about connecting with something fundamentally universal, bridging the gap between what we know and what might be. The light we see from the Sombrero Galaxy today began its journey 31 million years ago, traveling across the silent expanse of space to reach our eyes. During that time, life on Earth evolved from early mammals to the dominance of humans. This simple fact, that light serves as both a messenger and a time machine, underscores the profundity of astronomical observation. Every photon captured in our telescopes carries with it the history of the galaxy, encoding events we are only now beginning to decipher. The intricate balance that allows galaxies like the Sombrero to exist is awe-inspiring. Gravity pulls stars inward, binding them into their orbits, while angular momentum prevents collapse, maintaining the graceful structure we observe. But beneath this apparent order lies chaos. Stars are born from collapsing clouds of gas, while others meet fiery ends as supernovae, scattering their enriched remains across the galaxy. These explosions forge the heavy elements essential for life, spreading them into interstellar space to be incorporated into new stars, planets, and perhaps even living beings. Every atom in your body was once part of a star that lived and died billions of years ago. This cosmic recycling connects us not just to the Earth but to the stars themselves. The Sombrero Galaxy's dust lane, dark and enigmatic, is more than a striking visual feature, it's a dynamic region where stars are actively forming. But why does the galaxy's star formation appear subdued compared to more active galaxies? Is it nearing the end of its life cycle as a star-forming system? Or is it in a delicate equilibrium, sustaining itself without the dramatic bursts of energy seen in younger galaxies? These questions are not just about understanding M104, they are about comprehending the life cycles of galaxies as a whole. The halo of the Sombrero Galaxy, vast and filled with ancient globular clusters, is another source of fascination. These clusters contain some of the oldest stars in the universe, formed when the cosmos was young and dominated by primordial gas. Studying them is like looking at a photograph of the universe in its infancy. What stories do these stars tell? What conditions led to their formation, and how have they survived for billions of years? The answers may reveal not just the history of the Sombrero but also the broader narrative of galactic evolution. Dark matter, the invisible glue that holds galaxies together, adds another layer of intrigue. The Sombrero Galaxy's rotation curve, how its stars move at various distances from the center, defies the predictions of Newtonian physics, pointing to the existence of dark matter. But what is dark matter? Is it composed of exotic particles, or does it hint at a fundamental flaw in our understanding of gravity? Experiments around the world are racing to answer these questions, but for now, the Sombrero remains a testament to the unseen forces that shape the cosmos. At its core lies a supermassive black hole, a gravitational monster whose presence defies comprehension. Unlike stellar mass black holes, which form from collapsing stars, these supermassive counterparts seem to have existed since the earliest epochs of the universe. How did they form so quickly? Were they seeded by the first stars, or did they grow through mergers and accretion over time? The Sombrero's black hole is relatively quiet today, but its past may hold clues to these questions. Could it have once been a quasar, blazing with energy as it devoured surrounding matter? And if so, how did it transition to its current dormant state? The Sombrero Galaxy also challenges our traditional classifications of galaxies. It exhibits features of both spirals and ellipticals, blurring the lines between these categories. This duality suggests a complex history, possibly involving mergers with smaller galaxies or interactions with neighboring systems. What processes led to this hybrid structure? Was it a slow, steady accumulation of matter, or a more chaotic series of events? Understanding these dynamics could reshape how we think about galaxy formation and evolution. Looking beyond the galaxy itself, we are reminded that it is part of a vast cosmic network. Galaxies are not isolated islands but are connected through the gravitational filaments of the cosmic web, a structure that spans the observable universe. The Sombrero Galaxy, nestled within the Virgo supercluster, interacts with this web, influencing and being influenced by its neighbors. These interactions, though subtle, leave lasting imprints, shaping the galaxy's evolution over billions of years. And yet, for all its grandeur, the Sombrero Galaxy is just one of trillions. Each galaxy, from the smallest dwarf systems to the largest ellipticals, tells its own story. Together, they form a mosaic of the universe, a tapestry woven with threads of light, matter, and time. The Sombrero is a single thread in this tapestry, but it is a thread rich with detail and meaning, a reminder of the complexity and beauty that defines the cosmos. As we continue to study the Sombrero Galaxy and its counterparts, we are not just learning about distant objects, we are uncovering the mechanisms that govern the universe itself. Each discovery, no matter how small, brings us closer to understanding the origins, structure, and ultimate fate of the cosmos. The Sombrero Galaxy is a beacon of wonder and a challenge to our intellect, inviting us to look deeper, think broader, and dream bigger. In its light, we find not just answers, but the inspiration to keep asking questions. The Sombrero Galaxy, though seemingly serene and static from our distant vantage point, is in reality a dynamic and evolving entity, a microcosm of the universe's ceaseless activity. Beneath its tranquil facade lies a realm where stars are born and die, where invisible forces like dark matter sculpt its shape, and where the echoes of cosmic history reverberate across billions of years. Its very existence challenges us to confront the profound mysteries of space, time, and the nature of reality itself. The supermassive black hole at the heart of the Sombrero Galaxy, with a mass exceeding 1 billion suns, is a gravitational colossus whose sheer presence shapes the galaxy around it. Despite its dormancy, it exerts an invisible but profound influence, orchestrating the motion of nearby stars and gas clouds. Scientists theorize that such black holes may act as cosmic regulators, their energy output capable of either fueling or quenching star formation. Could this black hole's quiet nature be a sign of a galaxy in equilibrium, or is it the calm before another epoch of activity? Observing its subtle gravitational effects allows astronomers to probe the depths of the unseen, peeling back layers of cosmic history encoded in the orbits of the surrounding stars. The dust lane that encircles the Sombrero Galaxy, striking against the bright core, is not merely a backdrop to this cosmic wonder, it is an active, ever-changing environment where the building blocks of stars and planets reside. Molecular clouds within the lane, dense with gas and dust, are the nurseries where new stars are formed. Yet, the conditions for star birth are precarious, dependent on a delicate balance between gravitational collapse and the disruptive forces of turbulence, magnetic fields, and radiation pressure. Observing this process in detail with advanced telescopes reveals the intricate interplay of physics that governs the creation of stars, shedding light on how galaxies like the Sombrero maintain their luminous populations over billions of years. Further out, the Sombrero's vast halo is a region of intrigue, filled with ancient globular clusters and an abundance of dark matter. These clusters are fossilized remnants of the early universe, their stars formed from the primordial gases that existed shortly after the Big Bang. Each globular cluster is a snapshot of cosmic time, and their varying compositions hint at the galaxy's complex history of growth and interaction. The Sombrero's halo is unusually rich in such clusters, suggesting it has undergone a unique evolutionary path. Did it absorb smaller galaxies during its formation, each contributing its own cluster population? Or did it form in isolation, building its halo through internal processes alone? One of the most tantalizing mysteries of the Sombrero Galaxy lies in its hybrid nature. Its bright, spherical bulge is characteristic of elliptical galaxies, while its thin, well-defined disk aligns with the properties of spiral galaxies. This duality defies easy classification, prompting questions about its formation. Did it begin as a spiral galaxy that later accumulated a massive central bulge? Or was it an elliptical galaxy that developed a disk through subsequent interactions? The answer may lie in the galaxy's stellar populations. By analyzing the ages, compositions, and motions of its stars, astronomers can reconstruct its evolutionary journey, piecing together a narrative that spans billions of years. Beyond the Sombrero Galaxy itself, its context within the larger universe adds another layer of fascination. Galaxies are not solitary wanderers, they exist within a vast and intricate web of matter and energy. The Virgo supercluster, where the Sombrero resides, is one of the largest known structures in the cosmos, its galaxies interconnected by the gravitational pull of dark matter. These cosmic filaments, invisible to the naked eye, form the scaffolding of the universe, dictating the motion of galaxies and the flow of gas between them. The sombrero's position within this web influences its evolution, as the gravitational tides of nearby galaxies subtly shape its structure and star formation activity. The discovery of dark energy has added yet another layer of complexity to the study of galaxies like the sombrero. This mysterious force, responsible for the accelerated expansion of the universe, permeates space and affects the trajectories of galaxies on cosmic scales. While dark matter binds galaxies together, dark energy pushes them apart, creating a delicate cosmic tug-of-war. Observations of the sombrero and its neighbors provide critical data for understanding the interplay of these forces, offering clues about the ultimate fate of the universe. Will the cosmos continue to expand forever, growing colder and darker as galaxies drift apart? Or will it reverse course, collapsing in a dramatic, big crunch? Despite the sombrero's apparent tranquility, its past likely holds tales of dramatic collisions and interactions. Galaxies frequently merge in the cosmic dance, their stars and gas clouds intermingling in events that can trigger bursts of star formation or feed central black holes. The sombrero's hybrid structure may be the result of such interactions, each one leaving behind subtle traces in the form of tidal streams, warped disks, or unusual stellar populations. Advanced imaging techniques, capable of detecting the faintest features, are beginning to uncover these hidden scars, providing a window into the chaotic processes that shape galaxies over time. In the search for life beyond Earth, the Sombrero Galaxy also plays a symbolic role. Within its disk, billions of stars may host planetary systems, some of which could harbor the conditions necessary for life. The discovery of exoplanets within our own galaxy has revealed a staggering diversity of worlds, from Earth-like planets in habitable zones to gas giants with exotic atmospheres. If planets in the Sombrero Galaxy share similar characteristics, they could be home to entirely different forms of life, shaped by the unique conditions of their environments. While direct exploration of these distant systems remains beyond our reach, their potential inspires us to continue searching for our cosmic neighbors. As technology advances, so too does our ability to study galaxies like the Sombrero in unprecedented detail. Instruments like the James Webb Space Telescope and the Extremely Large Telescope promise to revolutionize our understanding of the cosmos, allowing us to peer deeper into the universe and uncover the processes that govern its evolution. These tools will enable us to study not just the Sombrero's stars and gas, but the very fabric of space-time itself, probing phenomena such as gravitational waves and the nature of dark matter. The Sombrero Galaxy is more than a celestial object, it is a reminder of the vastness and complexity of the universe. It invites us to question, to explore, and to dream, challenging us to look beyond our immediate surroundings and consider our place in the cosmos. Each discovery about the Sombrero is a step closer to understanding the universe's grand design, yet it also serves as a humbling reminder of how much remains unknown. In its light, we find not just answers but the inspiration to continue the journey of discovery, fueled by the unquenchable curiosity that defines us as a species. The Sombrero Galaxy continues to captivate not just as a celestial wonder, but as a symbol of the universe's boundless complexity and mystery. The more we study it, the more we realize how deeply interconnected its components are, and how they reflect the larger processes at play throughout the cosmos. It is a galaxy that defies simple classification, a hybrid of elegance and enigma, inviting us to unravel its secrets. The galaxy's core, shining like a brilliant lighthouse in the dark sea of space, tells the story of incredible forces at work. Supermassive black holes like the one at the center of the sombrero are known to influence their surroundings in profound ways. Though this particular black hole is dormant now, scientists believe it may have once been an active galactic nucleus, a quasar so luminous that it could have outshone the entire galaxy for millions of years. Such energy bursts would have had the power to reshape the galaxy's structure, pushing gas outward and halting star formation while enriching the intergalactic medium with heavy elements forged in the stars. But why has the black hole gone quiet? Could it reignite in the future? Black holes feed on matter, and if new material, gas, dust, or even an entire star, wanders too close, the dormant giant could awaken in a spectacular blaze. Observations from the latest generation of X-ray and infrared telescopes may reveal signs of this slow-motion drama, showing subtle shifts in the black hole's environment that could signal its next act. The Sombrero Galaxy's unique dust lane is another source of intrigue. Dust, often thought of as a nuisance obscuring stars, is actually one of the most important ingredients in the universe. It is within these dense regions of gas and dust that stars are born. But why is the Sombrero's dust lane so sharply defined? Most spiral galaxies exhibit sweeping, winding arms rich in star-forming regions, yet the Sombrero's disk remains relatively featureless, almost minimalist. Could it be the result of a past merger that redistributed the galaxy's material into this unusual configuration? Or is it governed by internal forces, such as the gravitational effects of its dark matter halo or the influence of magnetic fields threading through its disk? The halo of the Sombrero Galaxy offers an entirely different perspective. Extending far beyond the visible disk, this halo is a vast sphere of influence, populated by ancient globular clusters and infused with dark matter. It is a treasure trove of information about the early universe. Each globular cluster, a compact group of stars bound by gravity, acts as a fossil, preserving the conditions of the universe as it was billions of years ago. These clusters formed before the Sombrero Galaxy itself took shape, providing clues to the processes that led to galaxy formation. One of the most compelling features of the halo is its connection to the concept of galactic archaeology. By studying the motions, compositions, and ages of the stars and clusters in the halo, astronomers can reconstruct the galaxy's formation history. They can identify remnants of smaller galaxies that were absorbed into the Sombrero over billions of years, tracing the paths of these ancient cosmic collisions. These mergers are not just violent events, they are also creators, seeding the galaxy with new stars, enriching its gas with heavy elements, and contributing to the growth of its central black hole. The Sombrero Galaxy's place within the cosmic web adds yet another layer of intrigue. This web, an intricate network of galaxies, dark matter, and intergalactic gas, is the universe's scaffolding, dictating the movement and evolution of galaxies on the largest scales. The Sombrero, situated within the Virgo supercluster, interacts subtly with its neighbors through gravitational forces. These interactions may strip away gas, ignite bursts of star formation, or leave faint tidal streams, ethereal trails of stars torn from other galaxies. Searching for these faint imprints requires the most sensitive telescopes, capable of detecting light billions of times fainter than the night sky. While the Sombrero Galaxy is a wonder in its own right, it also serves as a key to understanding broader phenomena, such as the nature of dark matter and dark energy. Dark matter, the unseen mass that holds galaxies together, is evident in the Sombrero's rotation curve, how its stars move at different distances from the center. The outer stars orbit far faster than they should based on visible matter alone, revealing the presence of a massive, invisible halo of dark matter. But what is this mysterious substance? Experiments on Earth are attempting to detect dark matter particles directly, while cosmological simulations use galaxies like the Sombrero to refine their models of how this invisible matter shapes the universe. Dark energy, even more mysterious than dark matter, governs the expansion of the universe itself. Observations of galaxies like the Sombrero provide critical data for understanding this enigmatic force. By measuring the distances and velocities of galaxies, scientists have discovered that the universe is expanding at an accelerating rate, driven by dark energy. The implications are profound. If dark energy continues to dominate, the universe could end in a big freeze, where galaxies drift so far apart that their light can no longer reach each other, leaving a cold, dark cosmos. Galaxies like the Sombrero may hold clues to how this process unfolds and what it means for the future of the universe. Yet, even as we grapple with these grand questions, the Sombrero galaxy invites us to consider the possibility of life beyond Earth. Within its disk, billions of stars may host planetary systems, some of which could have the conditions necessary for life. The search for exoplanets in our own galaxy has revealed a stunning variety of worlds, from Earth-like planets to gas giants with exotic atmospheres. If life exists in the Sombrero galaxy, it could take forms we cannot even imagine, shaped by environments vastly different from those on Earth. The idea that intelligent beings may be observing their version of the universe from within M104 is both humbling and exhilarating. As our telescopes become more powerful and our computational models more sophisticated, the mysteries of the Sombrero galaxy will continue to unfold. Each discovery adds a new layer to our understanding, not just of this particular galaxy, but of the universe as a whole. The Sombrero is a reminder that science is a journey, one fueled by curiosity and driven by a desire to explore the unknown. In its light, we are connected to something far greater than ourselves, a cosmos that is as vast as it is beautiful, as mysterious as it is inspiring. The Sombrero galaxy stands as a beacon in the night sky, urging us to keep looking upward, to keep questioning, and to keep searching for our place in this extraordinary universe. It is not just a galaxy, it is a reflection of the infinite possibilities that await us, a reminder that the greatest discoveries may still lie ahead. The Sombrero galaxy, M104, serves as a cornerstone for scientific research, offering insights into some of the most profound mysteries of astrophysics. From its unique structural features to the underlying forces that govern its evolution, the Sombrero represents a microcosm of the complex processes shaping the universe. Ongoing research into this galaxy not only enhances our understanding of its distinct characteristics but also sheds light on universal phenomena that apply to galaxies throughout the cosmos. Dark matter remains one of the most perplexing and significant subjects in astrophysics. Observations of the Sombrero galaxy's rotation curve provide compelling evidence for its existence. The stars and gas in the galaxy's outer regions orbit far faster than they should if only visible matter were present. This discrepancy suggests the presence of an enormous halo of unseen mass enveloping the galaxy. To probe this enigmatic force, scientists use sophisticated simulations that mimic the behavior of galaxies with varying dark matter distributions. By comparing these models to observations of the Sombrero galaxy, researchers refine theories about the properties of dark matter. Some experiments, like those conducted at the Large Hadron Collider or deep underground detectors, aim to directly detect dark matter particles, while others focus on its indirect effects, such as gravitational lensing. In the case of the Sombrero Galaxy, its massive halo bends the light of background objects, providing another way to study the elusive substance shaping its structure. The Sombrero's prominent dust lane is a site of ongoing star formation, though at a subdued rate compared to more active galaxies. Recent studies using telescopes like ALMA, Atacama Large Millimeter/Submillimeter Array, have revealed intricate details of the molecular gas within this lane. Molecules like carbon monoxide, CO, which emit radio waves detectable at millimeter wavelengths, serve as tracers for the cold gas essential for starbirth. These observations have highlighted pockets of dense gas where gravitational forces are overcoming internal turbulence, leading to the formation of new stars. Understanding why the rate of star formation in the Sombrero Galaxy is relatively low compared to other spiral galaxies is a critical area of research. It could be due to environmental factors, internal feedback from the galaxy's central black hole, or the influence of its dark matter halo. The Sombrero Galaxy's bright bulge and extended halo make it an excellent target for studying chemical evolution. By analyzing the light spectra of stars in these regions, astronomers can determine their chemical compositions, ages, and motions. This data provides a timeline of the galaxy's enrichment with heavy elements produced in supernovae and other stellar processes. The Sombrero's halo, populated with thousands of globular clusters, contains some of the oldest stars in the universe. These clusters are relics from an earlier era, formed when the universe was still dominated by hydrogen and helium. By studying their metallicity, the abundance of elements heavier than helium, researchers can infer the conditions of the early universe and the processes that led to the galaxy's formation. The bimodal metallicity distribution observed in the Sombrero's globular clusters suggests a history of both internal star formation and external mergers, providing critical clues about its evolutionary path. At the heart of the Sombrero Galaxy lies a supermassive black hole with a mass of approximately 1 billion suns. Studying this gravitational giant provides insights into the relationship between black holes and their host galaxies. Observations of the stars and gas orbiting close to the black hole reveal its mass and influence on the surrounding region. One area of interest is the role of the black hole in regulating star formation. Through a process known as feedback, energy released by the black hole can heat or expel gas, suppressing star formation. While the Sombrero's black hole is currently dormant, its past activity may have played a critical role in shaping the galaxy's structure. High-resolution X-ray and infrared observations are being used to search for evidence of past outbursts, such as shock waves in the surrounding gas or unusual chemical signatures. The Sombrero Galaxy's classification as a hybrid between a spiral and an elliptical galaxy makes it a fascinating subject for theoretical modeling. Spiral galaxies typically have prominent disks with well-defined arms, while elliptical galaxies are characterized by their spherical or oval shapes and lack of disk structures. The Sombrero, with its bright bulge and extended disk, exhibits features of both. Theories suggest that this hybrid structure may result from a combination of internal dynamics and external interactions. For example, a past merger with a smaller galaxy could have triggered the formation of the massive central bulge while preserving the disk. Alternatively, the Sombrero may have formed in a region with unusually high density, allowing it to accumulate both spiral and elliptical characteristics. By modeling the gravitational dynamics and chemical evolution of the galaxy, scientists aim to uncover the processes that led to its unique appearance. While the Sombrero Galaxy appears relatively undisturbed, researchers suspect that faint tidal features may exist, revealing evidence of past interactions with other galaxies. These features, such as stellar streams or warped disks, are the remnants of gravitational encounters that redistribute stars and gas. Detecting these faint signatures requires advanced imaging techniques, often at extremely low surface brightness levels. Upcoming telescopes, such as the Vera C. Rubin Observatory, will have the capability to detect these subtle features, providing new insights into the Sombrero's past. By studying tidal remnants, researchers can reconstruct the galaxy's interaction history and test theories about its growth through mergers. The Sombrero Galaxy also contributes to our understanding of the universe's large-scale structure and the role of dark energy. Observing its position and motion within the Virgo supercluster helps map the distribution of matter and the influence of cosmic expansion. The study of galaxy clusters, including the Virgo cluster, has revealed that the universe's expansion is accelerating, driven by a mysterious force known as dark energy. By measuring the Sombrero's redshift and comparing it to theoretical models, astronomers refine estimates of dark energy's properties. This research has profound implications for the ultimate fate of the universe, whether it will continue expanding forever or eventually collapse in a big crunch. Advancements in technology promise to transform our understanding of the Sombrero Galaxy and others like it. Instruments like the James Webb Space Telescope are capable of peering into the galaxy's dust-shrouded regions, revealing the birthplaces of stars and the dynamics of its central black hole. Ground-based observatories, equipped with adaptive optics, can resolve individual stars in the galaxy's halo, providing unprecedented detail about its oldest populations. Meanwhile, the next generation of cosmological surveys will map the universe in greater detail than ever before, placing the Sombrero Galaxy within the broader context of the cosmic web. These efforts will not only deepen our understanding of M104 but also provide a more complete picture of how galaxies evolve within the universe's vast and intricate network. The Sombrero Galaxy, with its striking appearance and scientific richness, is far more than a distant object in the night sky. It is a window into the processes that shape the cosmos. Each discovery about this galaxy serves as a stepping stone, bringing us closer to answering the grand questions of existence. How did the universe begin? What forces govern its structure and evolution? And what is humanity's place in this cosmic tapestry? The Sombrero Galaxy reminds us that science is not just a pursuit of knowledge but a journey of discovery, driven by an insatiable curiosity to understand the universe and our connection to it. The Sombrero Galaxy stands as a monument to the boundless intricacy and beauty of the universe. It is more than a distant, luminous object. It is a gateway to understanding the forces that shape existence on the grandest scales. From its enigmatic supermassive black hole to its serene halo populated with ancient stars, every aspect of M104 tells a story of cosmic evolution, interconnected with the broader tapestry of the universe. As humanity peers deeper into the galaxy's mysteries, the Sombrero continues to challenge our understanding, urging us to refine our theories and expand the horizons of what we know. Its unique structure blurs the boundaries of classification, revealing the interplay of gravitational dynamics, chemical processes, and cosmic collisions. It reminds us that galaxies are not static entities but living systems, evolving through cycles of creation and destruction, influenced by forces both visible and invisible. The Sombrero Galaxy also serves as a poignant reminder of our own place in the cosmos. Within its disk and halo are billions of stars, each with the potential to host planets, some perhaps teeming with life. It invites us to wonder, if intelligent beings exist somewhere in the galaxy, are they too captivated by the stars, asking the same profound questions about their origins and destiny? Science has allowed us to study this majestic galaxy in exquisite detail, yet it also humbles us with the realization that we have only scratched the surface of what remains to be discovered. The sombrero is not just a subject of study, it is a symbol of the limitless curiosity that drives us to explore, to learn, and to connect with the vastness beyond our world. In the coming decades, as new technologies and missions unlock deeper layers of the universe, the Sombrero Galaxy will remain a cornerstone of scientific inquiry, a celestial guide leading us toward answers about dark matter, dark energy, and the origins of galaxies. It reminds us that the universe is both a puzzle to solve and an endless source of wonder. Ultimately, the Sombrero Galaxy stands as a beacon, illuminating the infinite potential of human exploration. It inspires us to look upward, not just to admire its beauty but to embrace the challenge of discovery. In its light, we find the courage to ask the boldest questions, the persistence to seek the deepest truths, and the humility to recognize the profound interconnectedness of all things in the cosmos. It is a reminder that as we explore the universe, we are, in a sense, discovering ourselves, a small yet significant part of a vast, dynamic, and extraordinary whole. Messier 33, also known as the Pinwheel Galaxy, stands as one of the most captivating and enigmatic cosmic structures, inspiring awe among astronomers and stargazers alike. As the third largest member of the local group, after Andromeda, M31, and the Milky Way, it offers an unparalleled window into the processes shaping spiral galaxies. Nestled approximately 2.73 million light-years away, this celestial marvel is more than a collection of stars, it is a dynamic system that holds secrets of the cosmos' past, present, and future. At its core, M33 boasts a mesmerizing spiral structure, a cosmic dance of countless stars intertwined with vast swathes of interstellar gas and dust. Unlike its larger counterparts, it lacks a well-defined central bulge, a characteristic that has long puzzled researchers. This distinct morphology, often referred to as a flocculent spiral, suggests a less violent history than the grand spirals of Andromeda or the Milky Way. Scientists hypothesize that its relatively quiescent past has preserved much of its primordial structure, providing an exceptional lens through which to study galactic formation and evolution. One of its most striking features is its prolific star-forming regions. Among these, NGC 604 stands as a cosmic jewel, a sprawling nebula over 1,500 light-years in diameter, making it one of the largest H2 regions known. This stellar nursery teems with activity, where the gravitational collapse of gas clouds triggers the birth of massive, luminous stars. These newborn giants emit torrents of ultraviolet radiation, ionizing the surrounding gas and creating a brilliant display of light. NGC 604 alone has been a focus of numerous studies due to its size and complexity, making it an ideal laboratory for understanding the interplay between star formation and feedback processes. The abundance of neutral hydrogen in this galaxy further underscores its scientific significance. Radio observations have revealed an intricate network of gaseous filaments extending well beyond its visible disk, hinting at a vast, unseen reservoir of matter. This extensive hydrogen envelope fuels ongoing star formation and provides crucial insights into mass distribution. By studying the rotation curves of M33, astronomers have uncovered compelling evidence of dark matter, a mysterious, invisible substance that constitutes a significant portion of the universe's mass. Its relatively simple structure, devoid of a massive bulge, offers a clearer view of how dark matter influences the dynamics of spiral galaxies. Beyond its physical attributes, this spiral system plays a key role in the intricate gravitational ballet of the local group. Tidal interactions with Andromeda have left subtle imprints on its structure, such as warped outer regions and elongated stellar streams. These gravitational encounters may foreshadow a future merger, as simulations suggest that the two galaxies could collide long before the Milky Way becomes involved. Such events are not merely destructive but also creative, as they can trigger bursts of star formation and reshape the evolving structures. Advancements in observational technology have revolutionized the study of M33. From the Hubble Space Telescope to ground-based observatories equipped with adaptive optics, astronomers have been able to peer deeper into its heart, unraveling its stellar populations and chemical composition. Infrared observations have revealed hidden pockets of star formation and the distribution of interstellar dust. Meanwhile, X-ray studies have uncovered a population of compact objects, including neutron stars and black holes, remnants of massive stars that have reached the end of their life cycles. Its relatively close proximity makes it an ideal target for the search for exoplanets. While most planet-hunting missions focus on the Milky Way, this galaxy presents an intriguing opportunity to explore planetary systems in an entirely different environment. Detecting exoplanets here remains a challenge, given the distance, but ongoing advancements in telescope sensitivity and data analysis hold promise for future discoveries. Such findings could provide invaluable context for understanding how planetary systems form and evolve under varying cosmic conditions. In the realm of cosmology, M33 serves as a cornerstone for calibrating the cosmic distance ladder. Variable stars oscillates with a regular period, are crucial for determining precise distances to nearby galaxies. By refining these measurements, astronomers can improve estimates of the Hubble constant, the rate at which the universe expands. Discrepancies in this value derived from different methods remain one of modern astrophysics' most pressing mysteries, and this spiral system continues to play a pivotal role in the ongoing debate. This galaxy also holds a special place in the cultural and historical fabric of astronomy. Its discovery is often attributed to the Italian astronomer Giovanni Battista Hodierna in the 17th century, though it may have been observed by ancient stargazers long before telescopes existed. Charles Messier later catalogued it as M33 in 1764, solidifying its place among celestial objects of interest. Over the centuries, it has inspired countless observers, from amateur astronomers marveling at its faint glow through backyard telescopes to scientists unlocking its secrets with cutting-edge instruments. In recent years, M33 has become a focal point for citizen science initiatives, inviting enthusiasts worldwide to contribute to its study. Projects like Galaxy Zoo have enabled the public to classify its features, while online platforms allow users to analyze telescope data and identify transient phenomena, such as supernovae or variable stars. This democratization of astronomy not only accelerates scientific discovery but also fosters a deeper connection between humanity and the cosmos. As we continue to explore its mysteries, the significance of this spiral galaxy extends beyond the realm of science. It serves as a reminder of our place in the universe, a single species on a tiny planet orbiting an ordinary star, gazing at a vast, interconnected web of galaxies. Its intricate beauty and complex dynamics challenge us to expand our understanding of the cosmos and our role within it. Whether through the lens of a telescope or the pages of a research paper, this celestial marvel invites us to ponder fundamental questions. Where do we come from? What is our place in the grand structure of the universe? And what lies beyond the horizon of our current knowledge? The journey of discovery is far from over. Each new observation, each refined theory, brings us closer to unraveling the enigma of this spiral masterpiece. As technology advances and our curiosity deepens, we can only imagine what revelations await in its uncharted depths. From its radiant star-forming regions to its dark matter halo, from its gravitational interactions to its role in cosmic distance measurements, M33 stands as a testament to the enduring quest for knowledge, a pursuit that unites us across time and space. Often referred to as the star-spangled spiral, it remains an inexhaustible source of wonder. Its seemingly tranquil yet richly detailed structure is a living archive of cosmic history, each star and nebula a chapter in an ongoing story billions of years in the making. As we dive deeper into the specifics of its composition, we uncover a tapestry woven with not only the fundamental building blocks of the universe but also the potential to rewrite many long-standing theories about galactic dynamics and evolution. One of the most intriguing aspects of this system is its metal content, or rather, its relative scarcity of heavy elements compared to other spirals. Astronomers have discovered that the intergalactic Voyager, as it's sometimes called, exhibits a lower metallicity gradient than expected, meaning the proportion of elements heavier than hydrogen and helium remains relatively consistent throughout. This finding challenges conventional wisdom, which suggests that heavier elements, forged in the cores of stars and distributed by supernovae, accumulate more densely near a galaxy's center. The unusually flat metallicity gradient suggests a less turbulent history, with fewer mergers or interactions to disrupt and redistribute stellar and gaseous components. Its relatively pristine nature also makes it an ideal candidate for studying early galactic evolution. An abundance of blue, short-lived stars offers a window into the processes that dominated the universe during its more youthful epochs. These stars, often clustered in open stellar associations, provide invaluable clues about the initial conditions required for star formation. Detailed spectroscopic analyses of these regions have revealed a chemical fingerprint pointing to a system relatively unspoiled by the accretion of smaller, metal-rich galaxies, a feature that sets it apart from the more interaction-dominated histories of the Milky Way and Andromeda. Yet, even in its relative isolation, this spiral has not escaped the gravitational influences of its cosmic neighborhood. Subtle distortions in its outer region suggest that it is engaged in a delicate gravitational dance with Andromeda. These interactions may be responsible for the faint, extended disk of stars and gas surrounding it, a feature that, while difficult to observe, carries vital information about mass distribution in the enigmatic dark matter halo. The study of these outer structures has benefited immensely from advanced techniques such as weak gravitational lensing, which allows astronomers to map the invisible scaffolding shaping its evolution. The dark matter halo, sometimes poetically referred to as the invisible cloak, is one of its most enigmatic features. By meticulously measuring the rotation curves of stars and gas clouds, researchers have concluded that the majority of its mass lies not in luminous matter but in this mysterious, unseen component. Understanding the distribution and properties of this dark matter is critical for piecing together the puzzle of how galaxies form and evolve. Moreover, M33 serves as a natural laboratory for testing alternative theories of gravity, such as modified Newtonian dynamics, MOND, which propose different explanations for the observed discrepancies in galactic rotation. While the invisible cloak exerts its influence silently, this galaxy is anything but quiet when it comes to star formation. The disk is punctuated by myriad H2 regions, where intense ultraviolet radiation from young, massive stars ionizes surrounding gas clouds. These regions are often surrounded by stellar clusters in various stages of development, offering a timeline of stellar evolution that spans millions of years. By studying these clusters, astronomers can trace the life cycle of stars and the mechanisms driving their formation. The complex interplay of gravity, radiation pressure, and magnetic fields in these regions continues to challenge our understanding of the processes shaping galaxies on both small and large scales. Among its most fascinating discoveries are its population of variable stars. Cepheid variables, in particular, have proven invaluable as cosmic distance markers due to their well-defined period-luminosity relationship. The presence of numerous Cepheids has allowed astronomers to refine measurements of its distance with unprecedented precision. Additionally, the galaxy harbors a wealth of other variable stars, including RR Lyrae stars, long-period variables, and eclipsing binaries. These stars not only provide a deeper understanding of structure but also serve as critical benchmarks for calibrating distances to more remote systems. Its relationship with Andromeda has long been a topic of intense study. The two are connected by a tenuous filament of gas, a remnant of past interactions that hints at their shared history. This filamentary bridge, barely visible even with the most sensitive instruments, is a testament to the intricate gravitational interplay shaping the local group over billions of years. Simulations of these interactions suggest that M33 and Andromeda have exchanged material on multiple occasions, enriching each other's star-forming potential while subtly altering structural dynamics. As we look ahead, its future is inextricably tied to the destiny of the local group. Over the next few billion years, it is expected to experience a series of increasingly close encounters with Andromeda, culminating in a dramatic merger. This cosmic event, though seemingly cataclysmic, will ultimately give rise to a new galaxy, blending stars, gas, and dark matter into a unified whole. Observing M33 in its current state offers a rare opportunity to study a system on the cusp of such a monumental transformation. Technological advancements promise to deepen our understanding in the coming decades. The James Webb Space Telescope, JWST, is poised to revolutionize our view, probing cooler regions in exquisite detail and revealing previously hidden aspects of the interstellar medium. Meanwhile, next-generation ground-based observatories such as the Extremely Large Telescope, ELT, will push the boundaries of resolution and sensitivity, uncovering faint stellar populations and mapping dynamics with unparalleled precision. In parallel, the search for signs of life remains an intriguing, albeit highly speculative, frontier. While the chances of detecting extraterrestrial civilizations here are exceedingly slim, its abundant star-forming regions and relatively stable environment make it an intriguing candidate for astrobiological studies. Advances in radio astronomy, such as those enabled by the Square Kilometre Array, SKA, could one day allow us to search for artificial signals emanating from distant civilizations, expanding the horizons of humanity's quest to answer the age-old question: are we alone in the universe? Ultimately, the enduring allure of this galaxy lies not only in its scientific richness but also in its ability to inspire. It stands as a beacon of the unknown, a reminder that the universe is vast, complex, and full of surprises. Whether through the lens of cutting-edge telescopes or the imaginations of those who dream of distant worlds, it continues to captivate, inviting us to explore, to learn, and to marvel at the boundless wonders of the cosmos. The galaxy known as Messier 33 continues to captivate humanity's imagination, serving as both a key scientific target and a source of cosmic wonder. Its intricate structure, evolutionary history, and dynamic interactions offer a boundless reservoir of mysteries for astronomers and theorists to unravel. Often referred to as the cosmic tapestry or stellar canvas, this spiral system demonstrates the profound diversity and complexity of galactic evolution, revealing truths that extend far beyond its 2.73 million light-year distance from Earth. Renowned for its elegantly designed flocculent spiral arms, M33's structure is less tightly wound than those of Andromeda or the Milky Way. These arms, woven with interstellar gas and dust, cradle stellar nurseries teeming with activity. Unlike galaxies with prominent bulges, such as Andromeda, its central core is modest, almost understated, consisting of older stars glowing faintly in the blue-white spectrum. This structural simplicity is deceptive, as beneath this tranquil appearance lies a hotbed of activity that holds answers to some of astrophysics' most enduring questions. One of the standout features of this system is its extraordinary rate of star formation, occurring at levels disproportionate to its relatively modest mass. The so-called stellar forge of M33 has puzzled scientists for decades. Why does it form stars so efficiently compared to others of similar size? Studies have pinpointed its abundant reservoirs of cool molecular hydrogen as a key driver. Observations with radio telescopes, such as the Very Large Array, VLA, have revealed vast regions rich in this star-forming fuel. Unlike the Milky Way, where such gas is confined to the inner disk, the stellar canvas extends its molecular material far into the outer arms, suggesting a dynamically stable environment capable of sustaining star formation over billions of years. Among its stellar factories, the region known as NGC 604 takes center stage. Spanning over 1,500 light-years, this immense H2 region is a breeding ground for massive stars, rivaling even the largest stellar nurseries in the Milky Way, such as the Tarantula Nebula. These newborn giants, often more than 50 times the mass of the Sun, burn through nuclear fuel at astonishing rates, emitting ultraviolet radiation that ionizes surrounding hydrogen gas. This process creates a glowing nebula whose intricacy has been likened to cosmic lacework. What makes NGC 604 particularly significant is its resemblance to star-forming regions found in the early universe. Studying this nebula allows astronomers to better understand how galaxies like M33 might have appeared in their infancy. The system's vast population of young stars is accompanied by an impressive collection of older stars, primarily residing in the central region and inner arms. These include red giants and ancient globular clusters, providing a fossil record of the galaxy's earliest epochs. Through their chemical compositions, astronomers can piece together a timeline of formation and enrichment processes. For instance, the low metallicity of older stars suggests an origin in a relatively isolated environment, free from significant mergers or accretion events that might have disrupted early development. Its relationship with Andromeda is a story of gravitational intrigue. Observations suggest that the two galaxies have been exchanging material for billions of years, a cosmic dialogue marked by subtle tidal distortions and shared gas streams. The discovery of a faint hydrogen bridge connecting them has fueled speculation about their intertwined history. Computer simulations suggest that a close encounter several billion years ago likely influenced the spiral structure and contributed to its robust star formation. These interactions are not merely relics of the past but continue to shape the dynamics of the local group today. While much of the focus has centered on the luminous disk, its dark matter halo remains one of its most perplexing attributes. Like most galaxies, the majority of its mass resides in an invisible component, inferred through gravitational effects. Unlike the Milky Way, which boasts a more complex dark matter halo due to a rich merger history, M33 offers a cleaner system for studying this elusive substance. Detailed measurements of its rotation curve have revealed an unexpectedly smooth distribution of dark matter, challenging theoretical models and suggesting that its properties may vary across different galaxies. Another fascinating feature is its collection of X-ray sources, including neutron stars, black holes, and supernova remnants. These objects, remnants of massive stars that have reached the end of their life cycles, are scattered throughout the system, often clustered in regions of active star formation. By analyzing their X-ray emissions, astronomers can probe extreme physics governing these dense objects, from the nature of accretion disks to the behavior of matter under intense gravitational forces. The discovery of ultraluminous X-ray sources, ULXs, has further intrigued researchers, as these enigmatic objects may represent intermediate mass black holes, an elusive category bridging the gap between stellar mass and supermassive black holes. M33's proximity also makes it an invaluable testing ground for detecting exoplanets in other galaxies. While the vast distances involved make such detections extraordinarily challenging, advancements in microlensing and transit photometry have opened new possibilities. Detecting planets here would mark a groundbreaking milestone, offering insights into planetary formation and evolution under conditions different from those in the Milky Way. Such discoveries could even refine the search for habitable zones in galaxies beyond our own, expanding the scope of astrobiology into an entirely new domain. This system also plays a crucial role in understanding cosmic expansion. Its Cepheid variable stars and eclipsing binaries serve as critical benchmarks for calibrating the cosmic distance ladder, allowing astronomers to refine measurements of the Hubble constant. This value, which describes the rate at which the universe is expanding, remains a source of significant tension in cosmology, with different measurement methods yielding conflicting results. By improving distance estimates, astronomers hope to resolve these discrepancies and shed light on the underlying physics driving cosmic expansion. As we continue to explore its mysteries, M33's significance extends beyond the realm of science. It serves as a reminder of our place in the universe, a single species on a tiny planet orbiting an ordinary star, gazing at a vast, interconnected web of galaxies. Its intricate beauty and complex dynamics challenge us to expand our understanding of the cosmos and our role within it. Whether through the lens of a telescope or the pages of a research paper, this celestial marvel invites us to ponder fundamental questions. Where do we come from? What is our place in the grand structure of the universe? And what lies beyond the horizon of our current knowledge? The journey of discovery is far from over. Each new observation, each refined theory, brings us closer to unraveling its enigma. As technology advances and curiosity deepens, we can only imagine what revelations await in its uncharted depths. From its radiant star-forming regions to its dark matter halo, from gravitational interactions to its role in cosmic distance measurements, M33 stands as a testament to the enduring quest for knowledge, a pursuit that unites us across time and space. Technological advancements promise to deepen our understanding in the coming decades. The James Webb Space Telescope, JWST, is poised to revolutionize our view, probing cooler regions in exquisite detail and revealing previously hidden aspects of the interstellar medium. Meanwhile, next-generation ground-based observatories such as the Extremely Large Telescope, ELT, will push the boundaries of resolution and sensitivity, uncovering faint stellar populations and mapping dynamics with unparalleled precision. In parallel, the search for signs of life remains an intriguing, albeit highly speculative, frontier. While the chances of detecting extraterrestrial civilizations here are exceedingly slim, its abundant star-forming regions and relatively stable environment make it an intriguing candidate for astrobiological studies. Advances in radio astronomy, such as those enabled by the Square Kilometre Array, SKA, could one day allow us to search for artificial signals emanating from distant civilizations, expanding the horizons of humanity's quest to answer the age-old question: are we alone in the universe? Ultimately, the enduring allure of this galaxy lies not only in its scientific richness but also in its ability to inspire. It stands as a beacon of the unknown, a reminder that the universe is vast, complex, and full of surprises. Whether through the lens of cutting-edge telescopes or the imaginations of those who dream of distant worlds, M33 continues to captivate, inviting us to explore, to learn, and to marvel at the boundless wonders of the cosmos. Future missions and observatories promise to unlock even more of M33's secrets. The James Webb Space Telescope, with its unparalleled sensitivity in the infrared spectrum, will allow astronomers to peer through its dust clouds, revealing hidden stellar nurseries and the earliest stages of star formation. Meanwhile, next-generation radio telescopes like the Square Kilometre Array will map gas dynamics in unprecedented detail, offering new insights into the processes governing its evolution. These advancements will not only enhance our understanding of this spiral system but also provide a framework for studying galaxies across the cosmos. Ultimately, the allure of M33 lies not just in its scientific richness but in its ability to evoke a profound sense of wonder. As humanity continues to explore its mysteries, it serves as a reminder of the vastness and complexity of the universe. Its glowing arms, stellar nurseries, and enigmatic dark matter halo are more than just objects of study, they symbolize the unending quest for knowledge, inspiring us to look beyond our own galaxy and dream of what lies beyond. Often referred to as the stellar crucible, this system continues to surprise and inspire with its intricate dynamics, unique star-forming activity, and profound role in unlocking universal mysteries. One of its most fascinating aspects is the interplay between ancient cosmic history and ongoing evolution, creating a living portrait of the universe in transition. At the heart of its intrigue lies dynamic spiral arms adorned with an unparalleled abundance of massive star-forming regions. Unlike the tightly wound arms of the Milky Way, they appear diffuse yet richly detailed, hosting an almost theatrical display of cosmic creation. Its most famous H2 region, NGC 604, exemplifies this. Containing over 200 massive stars that are less than 5 million years old, this nebula emits an astonishing amount of ultraviolet radiation, lighting up surrounding clouds of gas in a dazzling display. Studying NGC 604 has allowed astronomers to trace the feedback mechanisms between young, hot stars and their environments. This interaction profoundly shapes not only local nebulae but the broader evolution of the galaxy itself. What sets M33 apart from its counterparts is the sheer efficiency and consistency of its star formation. While most galaxies exhibit declining star formation as they age, this one has defied expectations, continuing to convert gas into stars at rates rivaling much larger galaxies. Observations suggest that its interstellar medium is unusually stable, with turbulence levels low enough to allow gravity to dominate and trigger frequent collapses of gas clouds into new stars. This efficiency makes it an unparalleled model for understanding how gas-rich galaxies may have behaved during the universe's younger, more active phases. Adding to its fascination is a rich population of variable stars. These, particularly Cepheid variables and RR Lyrae stars, act as celestial lighthouses, their rhythmic pulsations providing astronomers with a means to measure distances across vast cosmic scales. Cepheids in M33 are among the most precisely studied in the local group, offering insights into both its internal structure and the broader scale of the universe. Their periodic luminosity variations have allowed scientists to refine distance measurements not only to this galaxy but to those far beyond, contributing directly to efforts to resolve the Hubble constant tension, one of modern cosmology's most debated puzzles. Beyond its stars, M33 is also a showcase of exotic celestial phenomena. Among its treasures are ultraluminous X-ray sources, ULXs, mysterious objects whose brightness exceeds what is typically expected from individual stellar remnants like neutron stars or black holes. Some ULXs are suspected to be intermediate-mass black holes, rare objects whose existence could bridge the gap between stellar mass and supermassive black holes. The mechanisms powering these ULXs remain a topic of intense research, as they might involve unusual accretion processes or even entirely new physics. A particularly tantalizing mystery is its vast, enigmatic dark matter halo. While dark matter is an essential component of all galaxies, shaping their structures and influencing their evolution, this system presents an unusually clean model for studying this phenomenon. Its lack of a significant central bulge allows for analysis with minimal interference from other structural complexities. Observations of its rotation curve, how stars and gas move at different distances from the center, have revealed the unmistakable signature of dark matter. However, the smoothness of the curve has challenged traditional models, hinting at the possibility of unknown properties or distributions of dark matter that may vary from galaxy to galaxy. This has placed M33 at the forefront of efforts to unravel one of the universe's most profound enigmas. Its gravitational relationship with Andromeda adds another layer of intrigue. Recent simulations suggest that this system is not merely a passive satellite of its larger neighbor but an active participant in a gravitational tango. Evidence of past tidal interactions, such as distorted outer structures and elongated streams of gas, point to a complex history of close encounters. These interactions may have influenced its spiral structure and even fueled ongoing star formation. The two galaxies are expected to continue their gravitational dance over the next several billion years, with M33 likely to merge with Andromeda long before the latter collides with the Milky Way. This cosmic collision, while destructive on the surface, will ultimately birth a new galaxy, blending the stars and dark matter of both systems into a single, larger entity. In addition to its physical and dynamic properties, M33 has become a key player in the search for exoplanets beyond the Milky Way. While most discoveries have been confined to our galaxy, the possibility of detecting planets in this distant spiral has intrigued astronomers. Techniques such as microlensing, which relies on the gravitational bending of light by massive objects, have opened the door to identifying planets in other galaxies. Although no exoplanets have yet been confirmed, its abundant star-forming regions and relatively stable environment make it a promising candidate for future detections. Often considered a hidden gem of the local group, this stellar system reveals an almost poetic balance between structural elegance and scientific complexity. Its loosely bound spiral arms, dotted with stellar nurseries, act as celestial canvases where the drama of star formation unfolds. Unlike its larger siblings, Andromeda and the Milky Way, this cosmic neighbor has experienced a less chaotic evolutionary history, making it a pristine example of galactic dynamics untouched by excessive interactions or violent mergers. One of its standout features is an extraordinary star-forming efficiency. Scientists have observed that it forms stars at an almost unmatched rate for its size. This has led researchers to dub it a stellar factory, where molecular gas is consistently transformed into new generations of stars. The ability to sustain such activity over billions of years can be attributed to extensive reservoirs of cold hydrogen gas, which fuel the ongoing birth of massive, short-lived stars that illuminate the spiral arms like cosmic beacons. Among these arms lies one of the most iconic regions, the massive H2 region known as NGC 604. This colossal stellar nursery, visible even from Earth with modest telescopes, is home to over 200 massive stars whose intense ultraviolet radiation ionizes the surrounding gas. This process results in an ethereal, glowing nebula that stretches over 1,500 light-years. NGC 604 dwarfs many similar regions, such as the Orion Nebula in the Milky Way. Astronomers often refer to it as a miniature version of the conditions that existed in the early universe, providing a glimpse into how the first galaxies may have formed. The vast wealth of variable stars also makes this system an astronomical treasure, acting as timekeepers and distance markers across the cosmos. Cepheid variables have been crucial in refining the cosmic distance ladder, providing astronomers with precise measurements not only to this galactic neighbor but also to systems far beyond. Its well-studied variable stars have played a key role in calibrating the Hubble constant, a measure of the universe's expansion rate, offering valuable insights into one of modern cosmology's greatest mysteries. Beyond its well-lit spiral arms, the luminous structure hides a darker, more enigmatic feature, a vast dark matter halo. This invisible component, which dominates the galaxy's mass, has been studied through its gravitational effects on the rotation of stars and gas. Unlike many others, this gravitational enigma displays an unusually smooth rotation curve, suggesting that dark matter is distributed in a way that challenges current theoretical models. This makes it a prime candidate for testing alternative gravity theories and exploring the elusive nature of dark matter, a substance that holds the key to understanding the universe's structure. It is also a hotbed of high-energy astrophysics. Ultra-compact X-ray sources, ULXs, scattered across its disk have intrigued astronomers, as their brightness defies conventional explanations. These luminous sources may represent intermediate-mass black holes, which are rare and poorly understood. By studying these objects, scientists hope to bridge the gap between stellar mass and supermassive black holes, shedding light on how such enigmatic objects form and grow over cosmic timescales. Gravitational interactions with Andromeda have left subtle yet discernible marks on its structure. These include warped outer regions and streams of gas connecting the two galaxies, remnants of past encounters that suggest an intricate history of tidal interactions. Such gravitational exchanges have shaped its current state and forecast its future. In billions of years, it is expected to merge with Andromeda, a collision that will forever alter the dynamics of the local group and reshape both galaxies into a single, massive elliptical structure. This dynamic system has also been considered a frontier for exoplanet searches beyond the Milky Way. Though detecting planets in such a distant system is extraordinarily challenging, the prospect is not beyond reach. Gravitational microlensing offers a promising method, and the abundance of young, luminous stars provides an ideal backdrop for such studies. Finding exoplanets here would expand our understanding of planetary systems and their formation under diverse cosmic conditions, hinting at the potential for life in environments vastly different from our own. What makes this spiral system even more compelling is its role as a laboratory for studying the universe's evolution. Its relatively simple structure, free from the complexities of a massive central bulge, allows astronomers to test theories about the formation and development of galaxies in isolation. This, combined with its proximity, has turned it into a cornerstone for modern astrophysics. Its interactions, star-forming processes, and variable stars are essential tools for unraveling mysteries that stretch across time and space. As technology advances, the shimmering forge of cosmic creation promises to reveal even more secrets. Observatories like the James Webb Space Telescope and the Extremely Large Telescope are poised to dive deeper into its star-forming regions, unveiling hidden populations of stars and mapping the intricate dance of gas and dust that drives its evolution. It will also benefit from upcoming radio and X-ray observatories, which will explore its dark matter halo and high-energy phenomena with unprecedented precision. Ultimately, this celestial enigma stands as a testament to the universe's boundless complexity and beauty. From its luminous spiral arms to its invisible dark matter halo, the galactic canvas invites us to explore, question, and dream. It serves as a reminder of how much remains to be discovered, not only within its boundaries but across the cosmos. As our gaze extends further into the stars, this spiral marvel remains a guiding light, inspiring humanity to reach for the unknown and uncover the secrets of existence itself. Nestled just over 2.7 million light-years away, this wanderer continues to challenge and inspire as one of the local group's most dynamic and mysterious members. Its unassuming size compared to Andromeda or the Milky Way hides a realm of intricate astrophysical phenomena that ignite the imagination. This galactic neighbor, with its breathtaking flocculent spiral arms and unique evolutionary story, holds the key to unraveling some of the universe's mysteries, ones that stretch beyond the limits of human understanding. One of the most extraordinary aspects of the celestial architect is its enigmatic relationship with Andromeda, the dominant force in the local group. Observations have revealed faint tidal streams of gas and stars stretching between the two galaxies, evidence of gravitational interactions spanning billions of years. The slow, cosmic ballet between these celestial giants is a dance of disruption and creation, profoundly shaping the intergalactic sculpture's structure and future. Computer simulations suggest that the stellar drifter has orbited Andromeda for eons, its gravitational pull subtly altering its trajectory and sculpting its spiral arms. These interactions may even have triggered bursts of star formation, giving rise to the luminous regions scattered across its disk. Yet, the future of the galactic weaver is just as fascinating as its past. Within the next several billion years, its gravitational bond with Andromeda will tighten, pulling the two galaxies closer together. Astronomers predict that this will culminate in a dramatic merger long before Andromeda collides with the Milky Way. This apocalyptic event, while seemingly destructive, will forge a new galaxy, blending their stars, gas, and dark matter halos into a harmonious whole. The beauty of such cosmic transformations lies in their duality. The destruction of old structures leads to new ones, reminder of the universe's cyclical nature. The radiant spiral, however, is more than a future participant in a galactic collision, it is a living cosmic laboratory, where the laws of physics and the forces shaping the universe can be observed in action. Its unusually abundant reservoirs of neutral hydrogen gas, extending far beyond its visible disk, fuel its prolific star-forming activity. This extended gaseous halo serves as the raw material for creating stars and offers vital clues about how the stellar choreographer interacts with its environment. Astronomers believe these reservoirs may represent remnants of ancient cosmic filaments, vast streams of matter that once served as the scaffolding for early galaxy formation. Among the cosmic artisan's greatest mysteries is its role as a beacon for studying dark matter, the elusive substance that dominates galactic mass yet remains undetectable through traditional means. The rotation curve of the galactic sculptor, meticulously measured through radio and optical observations, tells a story of an invisible mass enveloping the galaxy. Unlike systems with prominent bulges or recent merger histories, the celestial enigma offers a relatively undisturbed platform for studying the distribution of dark matter. Its smooth, steady rotation challenges conventional models of dark matter halos, hinting at new physics that could one day rewrite our understanding of the cosmos. But the mysteries of the luminous nomad extend beyond its dark matter halo and into its starry heart. Its extraordinary collection of star clusters, variable stars, and supernova remnants provides a timeline of cosmic events spanning billions of years. Each of its globular clusters serves as a time capsule, preserving the chemical and dynamical history of the galaxy's formation. Meanwhile, its population of Cepheid variables plays a critical role in refining the cosmic distance scale. These pulsating stars, with their predictable brightness variations, allow astronomers to measure distances with stunning precision, making the starry architect a cornerstone in solving the Hubble constant debate. Beyond its role in cosmic measurements, the stellar forge is a hotbed of high-energy phenomena. The presence of ultraluminous X-ray sources scattered throughout its disk raises tantalizing questions about the nature of black holes and their formation. These ULXs are brighter than expected for typical stellar mass black holes, suggesting they may host intermediate mass black holes, elusive objects that bridge the gap between stellar mass and supermassive black holes. Alternatively, some ULXs may represent exotic binary systems where compact objects accrete matter at extraordinary rates, defying the limits of conventional physics. In recent years, the nebular Voyager has become a focal point for cutting-edge technology in astronomy. The James Webb Space Telescope promises to unveil new layers of its story, peering through interstellar dust to uncover hidden stellar nurseries and faint populations of stars. Meanwhile, next-generation radio observatories like the Square Kilometre Array will map its gas dynamics in exquisite detail, revealing the gravitational influences shaping its structure and the intricate processes fueling its star formation. Even more futuristic missions aim to push the boundaries of what we can learn from the celestial wanderer. Efforts to detect exoplanets in other galaxies may one day include this spiral marvel. With advanced microlensing techniques, astronomers hope to identify planetary systems orbiting stars within its spiral arms, offering a tantalizing glimpse into the possibility of life in entirely different galactic environments. While such detections remain speculative for now, the idea of finding Earth-like worlds orbiting distant suns in the stellar tapestry is a thrilling frontier for the future of astrobiology. The northern pinwheel, as it is sometimes romantically called, also serves as a gateway to understanding galaxy evolution within the local group. Its interactions with Andromeda, its seemingly unquenchable star formation, and its pristine structure make it a bridge between isolated dwarf galaxies and massive spirals like the Milky Way. By studying its unique characteristics, astronomers hope to answer questions about the life cycles of galaxies, from their formation in the early universe to their eventual mergers and transformations billions of years later. Ultimately, this cosmic wonder is a living storybook of galactic evolution. It invites us to ponder questions that transcend science and enter the realm of philosophy. What role does it play in the grander tapestry of the universe? How does its quiet beauty, shimmering in the vastness of space, reflect the intricacy and fragility of existence itself. As we continue to explore its mysteries with ever-advancing technology, the Cosmic Maestro reminds us of the boundless depths of the cosmos, a universe full of wonders waiting to be discovered, each more surprising and inspiring than the last. The Cosmic Voyager, as this spiral galaxy is sometimes affectionately called, continues to expand the horizons of our understanding of the universe. Its role as both a scientific marvel and a philosophical beacon is unmatched, offering insights into the nature of galaxies and the forces that govern them. At every scale, from its vast dark matter halo to the smallest flickers of newborn stars, the stellar symphony provides a stage where the cosmic ballet of creation, destruction, and renewal plays out in awe-inspiring detail. One of the most fascinating ongoing areas of study in the spiral jewel involves its intricate interstellar medium. The gas and dust within this system are not just the building blocks of stars, they also serve as a record of interactions and internal processes. Recent observations using advanced radio telescopes have mapped the distribution of atomic and molecular hydrogen with incredible precision. These studies reveal a complex network of filaments, voids, and dense clouds stretching across its disk, tracing the influence of gravity, turbulence, and magnetic fields. The presence of these structures raises intriguing questions. How do such patterns emerge? What role do they play in the formation of stars? Could similar structures exist in more distant and less accessible galaxies? The nebular enigma also stands as a testing ground for one of the most profound mysteries in modern astrophysics, the nature of dark matter. While its rotation curve, showing how the speed of stars and gas changes with distance from the center, matches the predictions of dark matter models, certain subtleties challenge our understanding. For instance, its halo appears to extend far beyond its visible disk, with a smoother distribution than expected for a galaxy of its size. Some researchers speculate that this discrepancy might hint at new physics, perhaps involving self-interacting dark matter or other exotic particles yet to be discovered. The luminous sentinel also reveals its secrets through the extraordinary light of its variable stars, a celestial clockwork that has helped refine the scale of the universe. Beyond the Cepheid variables central to distance measurements, other types, such as RR Lyrae stars, long-period variables, and eclipsing binaries, offer complementary insights into its structure and history. RR Lyrae stars, for example, are particularly useful for studying the oldest stellar populations of the spiral nomad, providing a direct link to its earliest epochs. This starry wonderland also contains clues about the explosive ends of massive stars. Supernova remnants scattered throughout the galactic tapestry serve as markers of past cataclysms, where dying stars expelled their enriched material into the interstellar medium. These events play a crucial role in shaping its chemical evolution, seeding it with heavy elements that later become the building blocks of planets and, potentially, life. Some remnants have been found to harbor neutron stars or pulsars, exotic objects that offer a glimpse into the most extreme states of matter. Yet, the intergalactic muse is far from a galaxy frozen in time. Observations of its kinematics reveal ongoing accretion, where streams of gas fall into its structure from the surrounding cosmic web. These inflows provide fresh material for star formation, replenishing its reserves and sustaining its activity over billions of years. Such inflows are a critical part of a galaxy's life cycle, and the stellar enchanter offers a rare opportunity to study them in detail, thanks to its proximity and relative isolation. Another exciting frontier in the study of the starry Voyager involves its massive star clusters, particularly open clusters scattered across its spiral arms. These clusters represent different stages of stellar evolution, from blazing hot blue giants in newly formed regions to cooler, older stars in more mature groups. By analyzing these clusters, astronomers can reconstruct its star formation history, revealing bursts of activity that may have been triggered by interactions with Andromeda or other nearby systems. The gravitational relationship between the cosmic artisan and Andromeda remains a subject of deep fascination. Some researchers believe that the galactic sculptor may have originally been a satellite of Andromeda, ejected during a past close encounter. This scenario could explain some of its unique features, such as its flocculent spiral arms and extended gas envelope. If true, this history would make the northern spiral a cosmic wanderer, a system that has not only survived but thrived after being cast out from its original environment. As we peer further into the depths of the stellar nomad, the search for exoplanets within its borders grows increasingly compelling. While detecting planets in another galaxy remains an extraordinary challenge, breakthroughs in microlensing and advanced telescopes offer tantalizing possibilities. Could the spiral wanderer harbor worlds unlike anything we have imagined, orbiting stars in its spiral arms or ancient clusters? The thought of alien skies under a faraway sun, framed by the glowing light of its nebulas, fuels the imagination and pushes the boundaries of human exploration. The cosmic tapestry is more than a scientific treasure, it is a living reminder of the universe's infinite potential. Its glowing arms, dark matter halo, and vibrant star-forming regions speak to a cosmos that is dynamic, interconnected, and filled with beauty beyond comprehension. Each discovery made within the spiral luminary not only deepens our understanding of this galactic wonder but also connects us to the larger story of the universe, a story in which our own Milky Way plays a small but vital role. As humanity continues to push the frontiers of exploration, the marvelous spiral remains a guiding light, an enduring symbol of what lies beyond. It whispers of mysteries yet unsolved, of worlds yet unseen, and of knowledge yet uncovered. The journey of discovery through its starry expanse is far from over, and each new chapter reveals that the stellar beacon has much more to teach us about the cosmos, our place within it, and the boundless possibilities of the unknown. The celestial wonder, as this spiral galaxy is affectionately known, continues to reveal new layers of complexity with every technological advancement. This majestic structure serves as a microcosm of the universe's diversity, encapsulating phenomena that range from the fiery birth of stars to the quiet, unyielding influence of dark matter. It is a masterpiece of cosmic evolution, constantly evolving and interacting with its environment, and its mysteries